We will start in 1 minute so that everybody can join. Okay, so let us start with today's event. I welcome you all to our flagship event of the year, Eureka 4.0. And let's move on to next. Are people joining right now, Ishita?
Yes, but you can start.
Okay. So we at Thapar Amateur Astronomer Society welcome you all to our flagship event of the year, Eureka 4.0. So knowledge is limited, but imagination encircles the whole world. A beautiful quote said by Einstein. So let us today all cross all our barriers of imagination and try to learn new concepts and push ourselves to think out of the box and make the most of this day today. So it is so great that people from different cultures, different colleges like IIT Delhi, Triple IT Delhi, BITS Pilani, and various other colleges of North India have come together on a same platform to celebrate the love of astronomy. It is so beautiful that astronomy is such a wonderful thing that has brought people of different cultures together. And we at TASK, we celebrate different events and we organize different events and celebrate our love for astronomy to show that to basically show our love for astronomy through our events. And the event which we organize in a year are Eureka, which you are part of right now. So in Eureka, we organize different competitions, quizzes, and lecture symposium like we are part of right now. And then we have Akash Ganga. In Akash Ganga, basically students of different schools join and learn new concepts so that and embark in them a new scientist, a future scientist, future generation scientists and engineers. And it's so great to be a part of that. And then we do have group discussions in which we express ourselves, we share our experiences, and it's so great to be a part of that. And we welcome you all.
Ishan, your mic is mute.
Sorry. Moving ahead, today we are joined by the faculty heads of this society, Dr. Debabrata Deb, who is the president of TAS and has specialization in computational physics, soft matter, and statistical mechanics. We are also joined by Dr. Mamta Gulati ma'am, who is the vice president of TAS and associate professor at Thapar Institute. We would like both of you to share your thoughts today.
Okay, hi everyone, good morning. Mostly this is a fine Sunday morning and everybody is relaxed, I suppose. And here joined to learn more about astrophysics, astronomy, and get some real good research input from the eminent speakers that we have in this morning. First, as already introduced, this society is a student society, so everything is run by the students. We are there just to guide them. So this whole, organizing these event and so many other events that we do every year, throughout the year, many events. I would suggest all of our participants to go through the website that we have, and you can just Google TAS and in Google Sites, and then you can get many more informations and other events that we have already organized. And just like today, we will organize many more, such events. So I would look forward to welcome you all in the other programs too. And I'm sure this today's program will also go in flying colors. Uh, so right now, I would like to not only welcome everybody all on board. Also, special thanks to our speakers who have agreed to, share their knowledge accumulated over several years. And first, I will welcome Dr. Brijesh Kumar, who would speak on optical spectroscopy related to astrophysics. I'm also looking forward. I personally have not done, I have done my academics in physics, but not much in astrophysics. But the love for the subject is there in my heart, and that's how I'm here in this group. Like many other students, I'm sure your paths will also cross directly with astrophysics and searching for new information, new science, new physics into it. But above all, I believe that love for astrophysics is not just for astrophysics. It has a greater purpose. It has a greater influence in the society, in our mind, in our daily life too. It gives us that grand vision that we can have, and that's different. That makes the subject different, astronomy and astrophysics, from all other subjects, even within the range of all the other physics subjects. And so with this short introduction, I welcome you all. And again, thank you, Dr. Brijesh Kumar, and also other following speakers, Vishwajit Paul and Nisim Kanikar, who will follow in this morning and also in the afternoon. So go ahead and learn something new. Thank you very much.
Mamta ma'am is also with us. Mamta ma'am, if you would.
Yeah. Hello, everyone. I first I would like to extend my warm welcome to all the participants and especially to our speaker, Dr. Brajesh Kumar. So thanks for your support in organizing the symposium. Uh, and as a part of the society, I joined the society some 3 years back from now, and it has been a very pleasant journey interacting with students on various platforms, like the graduate students, the postgraduate students, and the school students on various activities that we do. So my field of research and specialization essentially is astronomy and astrophysics. Particularly, I work on gravitational dynamics. But I would like to share one experience with you guys today. That's the first fascinating thing I learned about astronomy when I was in my graduate when I was doing my graduation in the in one of our physics courses, is that for example, everybody knows, we all know, and we we have been taught very early that it takes light 8 minutes to reach the surface of the earth. And then I realized later on that when we are on earth and observing something, the light takes finite amount of time to reach us. For example, our nearest star, uh, Al- alpha proc sorry the nearest star to us is sun, and the sun's light takes 8 minutes to reach us, as a simplest example. uh, so the activities that we see on earth right now have happened actually 8 minutes back on the sun. So imagine other objects which are many, many light years away from us. So the activities that we are seeing now have happened a lot of years back, some millions of years back on actually the surface of other galaxies and uh, other stars in our own galaxy and stuff like that. So that was the first and the first fascinating thing I learned about astronomy, and that took over my interest in astronomy. So I felt like sharing it with you guys. So, and regarding the today's symposium, so we have three sessions largely on spectroscopy, one concerning the optical spectroscopy, the X-ray spectroscopy, and the radio applications in spectroscopy. And we will also have a panel discussion at the end uh, in the after lunch session today on exoplanets. So I would like to welcome everyone on board and hope to have a very good session today and an interactive one, I must say. And let's start the activities and have fun. Thank you.
Thank you so much, sir and ma'am, for sharing your views. And
Pramit, just I want to have give one input.
okay, yes, sir.
Just share some normal guidelines once again with all the students, like
Yes,
as
sir.
you shared
Yes, sir.
in, yeah,
Uh,
like how to raise questions and when those questions will be answered, and also if they want to follow up with us or something, if you have any specific,
yes, sir. Yes, sir.
information
We
to
do
share.
have. Yeah, we do have a slide for that, and Ishita will guide us upon that.
Okay, thank
Okay,
you.
hello everyone. So I'll be telling you about the general guidelines that you have to follow throughout the event. First of all, please everyone enter with your full name so that we can keep track of your presence so that it's easy to provide you certificates later. The next thing is that it's mandatory to attend all the three lectures if you want the certificate of participation. In case we feel that your behavior is somewhat improper, you will be immediately removed from the meeting. So please, everyone, behave accordingly. Now, during the entirety of when the lectures are going on, you all will be put on mute. So, if you have any questions, you can just address them to the co-host named moderator. The co-host's name is task moderator. So you can just put your questions there and he'll keep track of your questions. Now at the end of each lecture, we have a 15-minute Q&A session in which uh, after he's kept track of your questions, he'll be putting them up with the lecturer so that there is ease and organization and all questions can be taken up. So if you have any questions, you can message them to the co-host named task moderator, and later on he'll be addressing your questions to the lecturers in the 15-minute Q&A session. Now, after we're done with all the lectures, there is also a panel discussion on search for exoplanets and alien life. In case you have any other queries, you can address them to any of the co-hosts. Yeah. So now I'll tell you about the schedule. We'll start with the first lecture at 10:30. That is Dr. Brijesh Kumar. He'll be giving the lecture on optical spectroscopy. It will be a 45-minute lecture and then a 15-minute Q&A session. Then at 11:30, we'll have the second lecture by Dr. Biswajit Paul on X-ray spectroscopy, and again a 15-minute Q&A session. Then we have lunch break from 12:45 to 1:45. And after that, we have another lecture by Dr. Nisim Kanikar on radio spectroscopy. And at the end of all these lectures, we have the panel discussion with Dr. Jasjeet. Okay, I'll tell you about this here. So we have the panel discussion with Dr. Jasjeet Bagla, Dr. Nisim Kanikar, and Dr. Biswajit Paul. And this will be moderated by Dr. Harvinder Jassal. This is on the topic alien life and exoplanets. Now, if you have any questions, regarding to this topic, you can address them in a form whose QR code is given here. You can also access the form. We'll be putting it in the chat box. So this is again for ease of organization so that during the panel discussion, there is not much confusion and all questions can be answered. So I request you all to just scan this QR code and enter your questions relating to the topic of our panel discussion, that is alien life and exoplanets.
The link of the form will also be given in the chat. So it's okay if you are not able to scan this QR code. You can just access the form through the link in the chat.
Okay, Ishita, I think also you can do is as the lecture progresses, like after half an hour, you can share this question link and the name of this or the username of the moderator. Like here it's written Q&A moderator or task moderator. Just pop this message after some time so that students don't like wonder about if they have missed this time, they can see it later too. Just send it in the chat box so they get informed.
Sure, sir. Sure, sir.
Yeah.
Okay, so now we would like to welcome Dr. Brijesh Kumar from Aryabhat Research Institute of Observational Sciences, that is ARIES. He is an expert in astronomy and astrophysics and specializes in the field of spectroscopy. So we welcome you.
Thank you, moderator. Can you hear me clearly?
Yes, sir.
Yeah. It's a very good morning here from Nainital. It is Nainital, and there is excellent weather today here, and a bright sun with the blue sky. And nights are also very clear. In fact, if you happen to be there in month of October and November in Nainital city, probably you will see star-studded sky. So it's wonderful to watch Milky Way. And also so many stars from the skies of Nainital. So I thank the organizers and the wonderful initiative I could hear. Bringing together all these young minds who can really think about the science and unlimited ideas about astronomy and related things. I especially thank Dr. Mamta and Dr. Devbrat, who contacted me to deliver this lecture on optical spectroscopy. So I'm going to share my screen. Yeah, anyone? Are you able to see my screen?
Yes, sir.
Yeah.
Yes, sir.
Yeah. So, so I'll be speaking today about optical spectroscopy. I am basically an astronomer at ARIES Nainital, optical astronomer to be specific. And what you see here in the top left corner of the slide is basically the white light turning into colors of light, from blue to red. And this is passing through a grating. So we will have a little bit introduction of optical spectroscopy, a bit of tools we'll discuss, and also a bit about data and science I'd like to discuss. Well, coming to the introduction. So what are the sources of electromagnetic radiation? Of course, particularly the spectrum. So what you see in this panel is that there are photoionization is the process which is involved in generating the X-ray photons, particularly when there is atom and you knock out the electrons from its orbit, I mean, the atom becomes ionized. So during this process, your X-ray photons are involved. Similarly, through Compton spectrum, there are long wavelength X-ray photons are involved over there. So these are very high energy photons, and during such processes, you get X-ray radiations. Now coming to the ultraviolet and visible wave bands, these photons you get through electronic transitions. I mean, from one state to another within an atom. Okay, when level changes. So this is what is depicted over here. So such processes are there. They generate UV and visible photons. Then coming to the infrared photons, which are less energetic, these basically involve molecular vibration happens. So that kind of energy level they're getting generated. Then coming to the microwaves, they are basically connected with the molecular rotation and torsion from that. So that kind of energy we get in from microwave. So this is the short of interaction of radiation and matter through which we get electromagnetic radiation. Of course, they starting from gamma rays to longer radio wave bands from here to here. So x-axis here, wavelength is mentioned, and on top frequency is mentioned, whatever you like. One thing I would also like to highlight here on the Y in this panel, there is a vertical column. So you can see that the large number of available energy states, they are available in ultraviolet and visible wave bands, where these photons are strongly absorbed. Okay, and the photons, for example, at long infrared and microwave wave bands, they are less available states, and they are almost transparent. So microwaves and other longer wave band radio waves, they are almost transparent. And you go higher wavelengths, so they are getting absorbed. So today we will focus mainly on this optical region, from roughly around 400 nanometer to 700 or 1000 nanometer. That is the kind of wavelength we will be discussing. Okay, what are spectrum types? Let us focus on that. So this is a source. This is a, you can assume that this is a sun, which is emitting black body radiation, and if you plot them as a wavelength versus intensity, so you will see a black body spectrum at a particular temperature. This depends only on temperature. Okay, so if you see through this, so this is how it is depicted. But suppose if there is a diffuse gas in front of this source, then you get some spectrum, something like this. You get absorption lines. So you can see these are absorption lines, and this is the absorption spectra. So these lines are seen over here. You just see these are in black. Here you just see in the continuous spectrum there are no lines. Here you see the lines. Now similarly, if you try to take spectra of directly this ionized gas, then you directly you do not get the continuum, but you directly get emission spectrum or emission lines. You just see there is no continuum over here. You are only getting emission lines. These are in red region, this is in a blue region. So this is called the emission spectra. So these are the three kinds of spectrum types we talk about: continuum spectra, emission spectrum, and absorption spectrum. So this kind of scenario is very good when the source is stationary. But we know that in the universe, all the stars, galaxies, they're moving all the time. So whenever there's a moving source, what happens? So this is the continuous spectrum. In the background we saw. So this is the rest frame lines, which are shown in black. Now when the source is receding from us, like moving away from us, then the wavelength getting red shifted. These lines are getting red shifted, and when it is moving towards us, then lines are getting blue shifted actually. So these are the key lines. This is a H alpha line, which is plotted 6563 angstrom hydrogen lines. This is H beta, this is H gamma lines. So this is a very important this is also, we know, Doppler shift of spectral lines. This is a very important information which is going to give us about the moving objects in the moving universe. Well, it is a very simple cartoon diagram of the spectrum. So we always plot an x-axis is the wavelength or frequency, and y-axis it is the flux or intensity we plot. So what matters when it comes to the spectra? Delta lambda. So that is the minimum separation we are able to do between two wavelengths. So what it means that this point actually collects photon which is having lambda range in this delta lambda. This is called resolution. Okay. Similarly, this particular point is having this kind of lambda range. Okay. This is how it is understood. Now let us talk about the spectral resolution. So this is delta lambda is basically called the spectral resolution. Okay, and this is defined by the Rayleigh's criterion. So you just see this is the blue wavelength. This is the certain lambda. It is shown over here, and lambda plus delta lambda. So this particular lambda is shifted by delta lambda in red. So this is delta lambda. Here it becomes the spectral resolution of a particular spectrum, right? Now, what is resolving power? Resolving power we define as the ratio of lambda by delta lambda. Okay, so this resolving power is dimensionless. Okay, and when you apply the Doppler shift formula, this delta lambda by lambda is equal to V by C. Okay, and this is applicable in the regime where velocity of the source which is moving away or coming to us is much less than velocity of light, C. So V is connected with resolving power R as a C by R. Well, spectrometry versus photometry, this is a typical kind of division we make. So on the first column, what we see is the delta lambda. This is the spectral resolution which we discussed. If it is greater than 300, then your resolution becomes around 10. This is of course on the optical range wavelengths I am talking about. This is called wide band photometry. In fact, our eye is also short of is a photometer. Okay, I would say, where this delta lambda is 1000 angstrom, because our eyes are sensitive to the entire optical waveband. Okay, so similarly, if it is you are reducing delta lambda to 300 to 90, then your R becomes 10 to 50. This is called intermediate band photometry. And 90 to 5 delta lambda, this is 50 to 1000, it becomes resolution, and this is a narrow band photometry we call about. Anything less than 5 angstrom, this is a typical, and resolution greater than 1000, this is called spectrometry. I mean, spectrometry is basically when you enter a regime where spectral resolution is about 5 angstrom or less. Okay, but this is a very rough division, and it is relative. So there are low resolution spectroscopy, for example, narrow band photometry is also called low resolution spectroscopy. Okay, well, this is a so there are category of spectroscopic investigation with a certain R you can do. Okay, for example, if your R is 10 to 100, okay, in this case you can probe the solid state features of any material, and molecular bands they come into play, and spectral energy distribution. So such things you can probe with a low resolution, low resolving power. If you're talking about R of around 1000, so you can probe some atomic features, and in fact you can also probe redshifts and high speed dynamics. In fact, suppose there's a galaxy very far away, it is moving with a speed of around this or even larger, 300 kilometers per second from us. Probably you need a resolution of 1000 to know its velocity. Okay, so that is the kind of physics you can investigate. Now, if you move further, let's say 10,000 resolution. This is relatively high resolution. You can probe objects which are moving with velocities of 30 kilometers per second. So here, in fact, you can study the line profile studies. You can do radial velocities of stars, stellar abundances you can prove. So about the celestial sources. Now further off, if you go about 1 lakh resolution, so in fact the motions as small as 3 kilometer per second you can prove. If you go, these are used mostly in molecular spectroscopy and also to prove interstellar medium lines where the motions are very less. I mean, due to less, random motions, right? So this is how the spectroscopic investigations are done in various R regimes. You see, one thing I would like to highlight here is when you are talking about R of around 10 to 100, if you go to the back slide, then 10 to 100 is basically belonging to the photometry regime. But again, this is photometry is nothing but a low resolution spectroscopy. So you should remember that, right? Well, there are some real spectrum I would like to show from my own work. You see, what you see here, you is a basically 10,000 degree Kelvin temperature of a star. It's the A to V type star. And what you see, this is the spectrum, and this spectrum is basically running from almost 3,500 nanometer to 1,000 nanometer, around that. So this is the continuum, and on top of the continuum, there are these absorption lines are there. You can see. So similarly, there is another star below here. This has a surface temperature of 20,000 degree Kelvin, and the continuum for this star is little different. Okay, and but this is also having some absorption features. So what are these absorption features? For example, our sun is having 6,000 degree Kelvin surface temperature, right? So we must have studied in your courses, physics courses, that there are lines, Lyman series of lines, Balmer series of lines, and Parsons series of lines. They are emanating from different excited states of atomic hydrogen. So Balmer lines, H alpha, this is the first line of that series, is 6563 angstrom. So 6563 angstrom, that line is appearing over here. You see, this is the Balmer line, and the last line is 36. This is second line, 4861. 4340, this is 4340. So this particular series of lines are Balmer series of lines in the spectra of stars. So this we predict from physics theory, and similarly there are, in fact, these are there are Lyman series, this Paschen series of lines, which you get over here in this particular region. These are Parsons series of lines. Similarly, Lyman series of lines you can get if you are having spectra somewhere here. So we can relate these absorption features of a real spectrum with the theoretical results. So so there are two things in this two plot. We see continuum and line absorption. Now let us have a look at the line emission. Here you see the spectrum is almost flat. So there is no continuum. You most of the time you keep looking at the lines. So that is why these are called line emission. This is a spectra from a nebula of gas near 865 micron. Now one more thing, we define a redshift, and the redshift is basically defined 1 plus z is lambda observed by lambda emitted, and this equals 1 plus b by c. And but when velocity of the moving object is close to the velocity of light, then your Lorentz factor is getting introduced. So this is how we mentioned the redshift. Redshift is also dimensionless parameter to gauge distance of celestial sources. Well, I will give you example of different R spectrum. This is the spectrum of a brown dwarf. Resolution for this spectrum is 150. This spectrum is there in the near infrared range. You can see lambda is roughly about 0.8 micron to 3 micron, I would say. So what do you guess? Is it an absorption spectrum or emission spectrum? It is an absorption spectrum. It is, you see, this is the short of continuum. I will add something like this. And what you see, so this is the CH4 H2O features are there appearing as absorption. Here again H2O absorption features appear over here. Similarly, H2O features they are appearing over here. So these are all broad absorption bands, I would say, in the spectrum of brown dwarfs. They are failed stars, I would say, brown dwarfs. Well, here is another spectrum of resolving power 2000. So what you see, these are the spectrum of globular clusters. So what you see in this picture is a galaxy at the center in black, and there are several, circles and cross. So circles are objects which are actually which are coming towards us. They are blue shifted, and with red color there are objects which are going away from us. In fact, the cross are going away, and the circles are coming towards us. So there is a simple example of this blue spectra on the top, and the red spectra and the red shifted spectra on the bottom. These are shown over here. So using this various lines, you can estimate the redshift. So what is happening over here? All these objects, they are there in the orbits around a galaxy. So if you measure radial velocity of those objects, you can see that what is the gravitating force of this particular galaxy, which is controlling the motions of these globular clusters, which are revolving around the galaxy center. So in fact, this is one way to study the dark matter in galaxies. Well, we will move further. We will go to a 48,000 R spectrum of a star. What you see, this is again the wavelength versus relative intensity on y-axis. What you see, so you can estimate the abundance of beryllium in a star. This is a star spectra of a star in the Milky Way. So what you see with the dotted one is the actual spectrum, and with the lines you see the fitted one with a variable abundance of beryllium. Okay, temperature of this particular star is 6600 degree Kelvin. So what you see in this way, we find that this particular observation is fitted with the abundance of 0.5 for beryllium very well. Okay, so this is how we estimate the abundance and the evolution of various elements in the universe by observing them in the star using a spectra. Well, this is a very high resolution spectra. I mean, zirconium oxide in a furnace. I mean, this is the kind of spectrum you see. And if you further take a close-up view, and again the close-up view, this is the x-axis, the wave number, y-axis, of course, intensity. You can really resolve the lines, individual molecular lines in this particular spectrum. Well, what are the type of spectral lines which are of interest for celestial sources? So there are different kind of celestial sources. They have their own intrinsic lines, as we stated in the beginning, that through interaction of radiation with matter, this is how it happens depending on the physical conditions. So there are celestial objects like stars, galaxies, planetary nebulae, supernovae, active galactic nuclei, and quasars. So in all these objects, these are certain lines which we, depending on the physical conditions, which we identify, we observe in this. For example, Balmer lines, hydrogen lines are most prominent, H alpha 6563 angstrom, then various Balmer lines. Objects, celestial sources, then lithium one, neutral lithium line 6707 angstrom, carbon, nitrogen, calcium 2 HK lines we get, calcium 2 triplet lines, sodium on D lines get an iron lines. So these kind of stellar lines which are available mainly from calcium and sodium. So sodium D1, D2 lines are very frequently observed from interstellar medium. So then there are interstellar bands, roughly the width, spectral width of 50 angstrom. That also we get at these wave bands. So in addition to this interstellar medium lines, we also get telluric absorption features, because after all, we are taking spectra of a star using a telescope which is situated on Earth, right? So the lines which are originating from atmosphere of the Earth, that also we observe along with the spectra. What are those? These are basically various bands we have already calibrated. These are basically due to oxygen, H2O, and water bands. So these bands need to be characterized to actually accurately determine the features of these astronomical sources lines, right? In addition to this telluric absorption lines, these are mostly appear in absorption, because I stated in the beginning that photons, most of the photons gets absorbed at the Earth atmosphere, even optical photons. Nebular emission lines, these are also, they also appear if your some elements ionized in a medium which is coming in the path of a star, then you will be getting nebular emission lines. So in addition to this, we also get background sky spectrum, because after all, when a light is reaching to us, then the background light along with that light is also reaching to us, right? So that spectrum is also, for example, solar absorption spectrum, mainly due to moonlight. If you are taking that, night sky emission lines, we get nebular emission lines and telluric absorption features. Of course, I discussed already, and interstellar absorption. So there are several backgrounds. So here, background sky spectrum is actually putting all these lines together, because we are mainly interested in the lines from stars and galaxies. That is why we call this background sky spectrum, and we are going to remove them to study this lines from stars and galaxies. Well, what all we can do? I mean, if you are having a colored picture of varying resolution of starlight, you can definitely using Doppler shifts, you can very accurately calculate the mass of two stars in orbit. And also you can discover exoplanets around stars, because if there is planet around a star, it is moving. So with that motion, there will be shift in wavelength, and by measuring the shift in wavelength, you can know that this star has some companion, and that could be exoplanets, right? So to discover exoplanet around a star, spectroscopy is a wonderful tool. Now, dark matter of galaxies, this also you can estimate, because as I stated that there are several objects which are revolving in a galaxy. Stars are one of them. There are star clusters, they also revolve in a galaxy. There are very many other objects we do not know. But when you observe a motion, then that motion is actually governed by the gravity which you are having, and the motion of those, or rather dispersion in motion of those objects surrounding galaxies, is reflects in Doppler shifts, right? Rate of expansion of the universe, of course, you can estimate by using standard candles like type 1a supernovae and Cepheids. We have standard candles. By looking at the light, we can tell at what distance they're situated using physical laws. So rate of expansion of the universe is also you can estimate using spectra. In addition to that, there are surveys, all sky surveys. In fact, as I told in the beginning, that all the objects, celestial objects in the sky, they are unmoved. So we would like to make a survey that with what velocity they're moving, whether they're coming to us, going away from us, or moving laterally. We would like to make inventory of velocities of all the objects in the sky. That's very important. In fact, you can make inventory of asteroids which are coming pretty close to us, maybe danger to life on Earth. Similarly, their chemical composition, we still do not know that from where we are getting all these elements. From all the elements in a periodic table, there are many many elements, I mean, mostly they originate from space. So chemical composition studies you can study using spectra from silicious sources. Well, now one portion of the presentation is over. Now I'm switching over the tools. There are very interesting stuff you can do, but you need tools to do that. So what is the tool? And we have been studying in the physics, I mean, various courses. You just see this is the diagram for a schematic spectrograph. So there is a light source of a star or a lamp. So it is passing through a slit, and if a plane parallel light passing through a prism, it produces color. Okay, this is the typical rainbow formation you can imagine. So this is a prism as a disperser you're using to disperse light in different colors. Then you can use gratings to disperse light. Then you can use both prism and grating, that we call grism. So these are the dispersing elements which you can use to disperse light, and this is the typical layout of an spectrograph. So what you are having, so the light is coming from a telescope. Of course you need a telescope because the stars are very far away from us and they're very faint, very faint. So to collect more number of light from those stars, you need a large aperture of a telescope. For example, at Nainital we are having India's largest optical telescope that is having aperture of 3.6 meter. So after collecting light from this telescope, you put all the light in this slit. Okay, so from the slit the light goes to the collimator mirror and the light is getting collimated. After getting collimated, it goes to the diffraction grating, then different colors are produced. Then we again have a converging lens. There's a camera mirror, I would say, or it can also be a lens, and then it focuses on detector, and you will have a spectra over here. Then that spectra will be ready to estimate the redshift and motion of objects, right? Well, now let us study a little bit about the telescope versus the spectrograph plane. So what you see here in the in this is a slit. Actually, when you are putting a star, this is a star on the slit. So this is the sky, upper and lower, and this is the object. So height of the slit is h and width is w. So this slit is exactly getting mapped into dispersing elements, be it prism, grating, or grism. And after getting mapped over here, we spread the light in different colors. So your x-axis, you just see, this is the dispersion direction, delta lambda. Okay, y-axis is basically your height of the slit. This h is getting converted into h prime. Okay, w is getting converted into w prime, because so when you are getting h to h prime, here only telescope plays a role, h prime by h. But when you are getting the width of this light getting converted into w prime, like spectral width, then your telescope plus spectrograph properties are getting reflected into that. So what all you get? So this slit, so you will get the light. So this is called the spectrum, object spectrum. You will get a skyline. If suppose there is a skyline, you'll get a skyline, and you'll get a sky spectrum. Okay, in the background, I will show you some real spectrum taken from a telescope and a spectrograph, right? So this is another picture, I mean, of a spectrograph which you see. Well, this is another spectrograph picture to demonstrate you that how it happens. So this is the objective. This is the objective. This collects light and it focuses on this slit. So here you can have a slit like this. So this slit width is 20 micron. I mean, this has to be, I mean, comparable to the wavelength, right, at the slit. So for the diffraction to happen, so this is the slit width. You can put a slit of different width over here. This goes for collimator. This is a collimator. Then the disperser element. Then this is the camera, and this is the focal lane, focal plane. And this is the detector at focal plane. This is how your spectrum looks like, right? This is on this. Well, as I stated earlier, there are various kinds of dispersers. Prism is, of course, we all know because during rainy season you must have seen rainbow formation from light from sun, and raindrops actually works as a prism. So prism is a typically low resolution spectrometer, dispersing element. Grating low to high resolution spectra can be achieved using grating. Using prism, low to moderate resolution spectra, because prism gives a low, so low to moderate resolution spectra can be achieved using prism. Then Fabry-Perot and Michelson interferometer and heterodyne. This is another technique using which you can generate dispersers, which gives white light into colors, right? So gratings are very popular and very productive, I would say. So this is the typical grating equation which you see. So this is m lambda is equal to d sine alpha plus sine beta into d, right? So d is the basically spacing separation. So typical gratings have about let's say low resolution grating I'll talk about. So 1200 lines per millimeter. So you can see at every micron level you will have a spacing. So d spacing is that. So when this is the incident angle alpha, and this is the grating normal. So this is for, and this is the beta, is the angle of diffraction. And so for constructive interference to take place, this is the grating equation. So m is the order of spectrum, and lambda comes to the play. So this alpha is shown over here. So for any given alpha and beta, this alpha and beta, the equation holds for many values of m and lambda. So m is basically, there are orders, there are different orders you can get, 1, 2, 3, 4, and different lambda range you can get. So this is a various lambda range and orders are shown over here. It depends on us how we are going to design spectrograph. What is our science requirement? Depending on that, we choose order and lambda range. And accordingly, alpha and beta are set so that this information goes into building a spectrograph. Well, this is another important parameter for any spectrograph. This is angular dispersion. Okay, number of angstrom units, they are getting projected in a certain physical unit, millimeter. This is what is angular dispersion. It is d beta by d lambda. So it is m by d cos beta. So if you want to have a larger angular dispersion, okay, then what you are going to do, either you have higher m, higher order, go for higher order, or you have a smaller d, smaller spacing between the gratings, rulings, or larger angles, larger angle of diffraction, that is beta. Okay, so one of these you can control and have this spectrum. Now there are other dispersers. This is prism ecal. This is mostly used for low resolution, as I spoke earlier, and the efficiency of this prism is very high since light is not diffracted into many orders. So we are getting very high efficiency and high signal to noise ratio. In fact, if you want to cover many objects, in that case also it is used. Well, this is a grism. Grism again is used for R value of 10 to 1000, and it can be used on axis in a camera or as a cross disperser by both methods. Well, ultimately, so suppose you have built a spectrograph, you would like to know that what is the value of R for this spectrograph. So this is the width if you take, and this is the width on the detector when you have spread the white light, and this is the disperser A. So so there's a little mathematics which you can very easily do, but here the important thing I would like to highlight is what all are the numbers which goes into this in estimating R. So R is basically lambda by delta lambda, and in estimating this value of R for a particular spectrograph, what goes in, basically it goes the objective diameter D, and this angular slit size is goes because yeah, this is where from where this light goes into the spectrograph, and the diameter of the collimator lens, that also plays a very important role, and then the angular dispersion of a spectrograph that we discussed already. So this is the final equation. It comes resolving power of any spectrograph. Of course, it depends on lambda. It depends on the diameter of the collimator. This, it depends on the angular dispersion of the spectrograph and the angular slit size phi, and it also depends on the diameter of the telescope or objective lens, right? So these are the factors in which this R depends on. So suppose, depending on the size case, you want to fix R. Okay, I want R of, let's say, 1000. Then suppose if R is fixed, then what you're going to do, either in that case, a larger telescope means larger collimator, right? Means bigger instrument. So if R is fixed, you have got to make this D larger. Aperture of telescope is larger, and D collimation then will also have to be larger. So it means that the bigger instrument you are going to build. Okay, so, and bigger the instrument, larger the cost. So this is how it goes: collimator diameter and objective lens diameter. Now, if you want to change R for a given telescope, it mostly happens that the telescope size, because telescopes are very costly to build, so telescope sizes are fixed. Okay, then you have no choice. When telescope size is fixed, depending on the resolution, your this size is fixed, collimator. Then what you are going to change? You are going to change angular dispersion of spectrograph, that is in your hand, or the slit size, angular slit size. So by changing angular dispersion, if you go from A to 2A, your spectra will become something like this. You'll be able to separate different lambda. Similarly, if you increase by half the angular size, you make it smaller, your spectra will be something like this, well separated. Okay. Well, what are the types of spectrographs? As I said, depending on the dispersing elements, we call it the objective prism spectrograph. We call it long slit spectrograph. Multi-object spectrograph, when there are you are collecting lights and having different slits, you are putting lights at each slit, and each slit is passing through spectrograph and taking a spectra. So this is called a multi-object spectrograph. Then there is an integral field spectrograph. Here, I mean, it's almost giving information about instantaneous information about every element motion along the path or in an area in the sky. That is the integral field spectrograph. So out of this long slit spectrograph, this is very popular. So you just see, this is the picture, what you see of a long slit spectrograph, optical spectrograph rather. It is called ATFOSC, at 3.6 meter Devastal optical telescope. So this is a faint object spectrograph come camera. What it means that if you want to use this spectrograph in a simple camera mode, you can use that. And it's needed that sometimes you would like to take the simply pictures, just like our eye is able to see the stars in the night sky. This camera is very sensitive, will be able to see stars and galaxies and record them. And after recording them, you would like to take spectra, I mean, by choosing. So this is how we built FOSC-like instrument, and these are workhorse instrument for optical spectroscopy on larger telescopes. So on 3.6 meter Devastal optical telescope, which is situated in Nainital district, we are having one such spectrograph, and this is the picture of a spectrograph you see. So this is the black portion. In fact, you can see this is the optical train of the spectrograph, including the disperser and the collimating lens and the camera lens and the detector. Detector is sitting at the end, and light is focusing somewhere here in the this focal plane, and the total length of this spectrograph is roughly about 1.5 meter. So you can imagine, and this whole spectrograph is very complex, and it is mounted at the back end of this telescope. So this telescope, this is a 4-meter class optical telescope, and typical height of this telescope is roughly 12 meter from here floor level to the top level. Okay, and this entire telescope is housed into a 10-story building. What you see here in the right panel is the dome for this telescope, and there's a slit just like eyelid in our sky to opens into the blue sky. And whenever we want to observe and night sky is clear, and then this dome rotates also, and so that wherever the telescope is pointing to the sky to any new star, your dome automatically moves to that, and then spectrograph collects light from that and takes a spectrum. So this is so suppose you are interested. I mean, this is the typical data you collect. I mean, data are always black and white, but the science is colorful, I would say. It's a very interesting science we estimate from this data. So what you see here in the left side, I've shown a galaxy, and there is a supernova, there's a bright star is shown over here. This is a supernova 1994D. So if suppose supernova occurs in a galaxy, this provides us an opportunity to estimate the distance of that particular galaxy where it happens independently. I mean, one way to estimate how far the galaxy is by using the redshift and Hubble's law. Another way is to estimate the distance to this galaxy is using a supernova as a candle. This is the type 1 is supernova which is happening. So we'll put this supernova immediately through a telescope, and we will take a spectra. So this is the spectra of this particular supernova, not this particular, but another supernova, I would say. So this spectrum appears something like this. So the slit is getting dispersed across lambda. So x-axis is lambda. So what you see, so these are skylines. You see, these are skylines, bright, which is across the entire slit. Okay, this is the light from a star. You can see there is a dimming in this light. It means this is absorption. Photons are getting absorbed at this particular point. So this 2-dimensional spectra actually is reduced into 1-dimensional spectra. So 1-dimensional is, of course, we have seen the wavelength on the x-axis and y-axis of flux. So x-axis here pixel is getting calibrated to wavelength in angstrom, and y-axis fluxes and counts are getting calibrated through physical units, right? So this is the typical spectra of a supernova. This is supernova 2008 GZ, and what you see, so continuum is hardly seen in this supernova. In fact, most of the cases you are able to see absorption lines over here, and based on these absorption lines, so we can know that from which elements these are originating, and by knowing the rest wavelength of these lines, we can immediately estimate the redshift, how far this object is from us, and also several other parameters of this supernova. Well, this is long slit spectrograph data again. So a very interesting information you are getting over here. So what you see here in this, this is the sky and galaxy you see here. So this is a spiral galaxy, in fact, and along this galaxy, this is the slit is placed, and the slit is demonstrated over here, and you get a spectra over here. So here what we see, we have converted wavelength on x-axis, y-axis we have radius, the center of the galaxy. So you can see we have taken spectra at every spatial element of the galaxy across the galaxy, and what you see is the larger from the galaxies, there are lines. For example, here there are lines, and here, and that particular spatial we have converted into velocities, kilometer per second. So you can see the upper portion of the galaxies, they are going away from us. Okay, and this portion, lower portion, this portion of the spectra is coming towards us. So every point here we are generating spectra, we are trying to estimate velocity. In this way, we are able to say that the galaxy's arms, they are rotating in which direction, which arm is going away from us and which arm is coming towards us typically. So that's a very easy to find out the motion of arms in a galaxy. This is a spiral galaxy. Well, there are, in fact, this is all, I mean, I collected all this information for this forum. And there are several very interesting literature where you can find observational aspects of spectroscopy. Observational Astrophysics by P. Lena. This is one book where I would say that you can find stuffs over there. Then Astronomical Spectroscopy by Jonathan Tanchin. He also mentions astronomy in general, spectroscopy in general. Then on particularly on long slit spectrographs, you can find by Chris Churchill. You can explore on the web. Astronomical Spectroscopy by Michael Cushing. This I liked. It's a very and Astronomical Spectroscopy by P. Massey and M. Hessian. So if you want to know that what all how the spectrographs are built, tools are built, and how they're used to probe the celestial sources, you can go through these references. Well, thank you very much. This is Himalayas seen from our Devastal site, Nainital. What you see over here. Thank you.
Thank you so much, sir. And we really appreciate your efforts, and we really thank you for presenting and giving your time to us. And it was a really great experience. Now I would request Ishita to kindly ask the questions of our participants to sir.
Thank you so much, sir, for your all the knowledge that you shared with us.
Yeah, thank you.
So Spandan Malik is asking, which type of optical spectroscopy is used to research solid and powdered physical samples?
Which type of spectroscopy for solids and
powdered physical samples?
Powdered physical sample. Well, this is not the area. I mean, my field of area for spectroscopy, we normally deal with the ionized regions, atomic label I deal, not with the solid state and powder things. I may not be the best person to comment on this, but of course, solid state features, I mean, with the low resolution spectroscopy, they are useful, but they only give you a very continuum level spectrum, broad spectrum. Probably you need to calibrate with the different solids and their spectra and the spectra for powders. Yeah. So that's what I of course, this is my guess. I mean, I'm not an expert on this field, right? We can take next question.
Rupinder Pal Singh is asking, how do we calculate the temperature of stars with such great accuracy? Just a second, sir.
Yeah, this is very interesting question. You see that it's a basically and also I would add that temperature of stars are very high. I mean, temperature at 300-degree Kelvin, the kind of temperature we are having on Earth, and the sun's surface temperature is 6,000-degree Kelvin. I mean, how you can, it's a very high temperature in addition to that. And also there are stars which are having temperatures 10,000-degree Kelvin, 20,000-degree Kelvin. In fact, there are much higher temperatures which we this week I call this, these are black body temperature, where thermal radiation we keep getting. So we simply apply black body laws to get this temperature. And when you plot Planck function, lambda versus flux is basically depends only on temperature. So that's a single parameter, and after getting spectrum, you can fit that particular temperature, and you estimate the temperature in that way. there are other ways also. There are some temperature sensitive lines, spectral lines of which originate from the atmosphere of stars. Those lines are also used to estimate very accurate temperature of stars. So one is of course the rough temperature. You simply need low resolution, rather you need photometric data plot point, and you generate a spectral energy distribution and try to fit a Planck into that. You get a very rough temperature, and if you want to estimate a very accurate temperature of this surface, probably you go to the spectral lines, and you need high resolution spectra for that. Hope this answers.
Uh, Spandan Malik is asking,
Yeah.
is the Lorentz factor only necessary for velocities tending close to C, or is it applicable otherwise too, but not taken due to approximation reasons?
Yeah, actually, Lorentz factor is, I would say it's always applicable. It's always there. I mean, the basic physics element, and that has to be there. And but for velocities, let's say redshift of up to 1, we have used supernovae to know that, look, our universe is not only expanding, but it is accelerating. So for lower redshift, I would say we need not invoke this Lorentz factor. But if you are interested in a very high velocity flows, and if you are interested in spectra of those high velocity flows, then there you invoke Lorentz factor uh, to get a correct velocity, right? So this is how it is done.
Uh, Abhinav Singh is asking, is the spectrum different for dwarf, giant, and supergiant stars? If yes, why?
Yeah, spectrum actually is they are different for these kind of stars. And first thing is, of course, it is mainly governed by temperature, uh, the spectrum. I mean, I would also say that when we say spectrum, I mean, there are two components. One is, of course, the continuum component. Another one is the lines. Okay, particularly absorption lines, and also in some cases emission lines. So so line broadening actually depends on the gravity. So at the surface of these stars, the gravities are different, so they affect the broadening of these spectral lines. And but when the temperature, surface temperature for those stars is same, be it of different class, you will be having the continuum of a similar nature. Okay, you'll be able to fit the same Planckian to all the spectral energy distribution. But when you are go to the spectral features, probably they depend on gravity. They also depend on metallicity. So those are very detailed features through which you distinguish whether it is a dwarf, a star, or whether it's a giant star or subgiant stars. Okay.
Yes, sir. Bandhan Goel is asking, what is a cheap and effective method to create parallel rays other than achromatic lens? Slit will cause scattering and diffraction.
Yeah, parallel. I think it's a simple pinhole can work very well. I would say, and it also it's very in lab. It is very difficult to create collimator. Suppose you are having a very, I mean, F9 beam. If you want to generate collimated F9 beam, you really need a very long effort. I mean, for that. So simple pinhole, I mean, should work. I mean, that's what I feel.
Arushi Chauhan wants to know, what does order M mean in angular dispersion?
Order. I think let me go there. So these are the orders actually at which the constructive interferences are happening. Okay, for if you are going to meet this criteria that you know they will rays will have to be in phase. Okay, so if that constructive interference criteria is met, it is decided by M. Okay, so this is how it happens, and it depends on also the spacing and other parameters of the grating, but order is basically giving the criteria for constructive interference to happen, right?
Spandan is asking, are the circles considered blue shifting with respect to the observer as a system or the center of the globular clusters or galaxies?
Yeah, this is a good question. Uh, Rather very good question. Actually, you whenever you see suppose this is a galaxy. This is a galaxy. Rather, I would say I would take this example. Yeah, this is a spiral galaxy which you see over here, and on top of that there is a slit. So it's spiral arms are getting wrapped around the center. So the center of the galaxy is moving with a different velocity, right? And with reference to that, the arms are moving. So that reference velocity of the center of galaxy need to be removed to know that, and this is a relative reference. The reference here we have set as 0. Okay, so it doesn't mean that your galaxy is moving with a 0 velocity. I think this is very good question. It is always the relative uh, motions in which we are interested. In many cases, if you want to understand the motion within a system.
Bandhan Goyal is asking, is LMT operational? How the mercury is prevented from evaporation?
Yeah, LMT liquid mirror telescope is right now it is not operational. All the elements are put together, and we will try to test it at the site very soon. And all the measures are taken to control the mercury vapors. And in fact, there are sensitive instruments. They are installed inside the ILMT building to measure the mercury level all the time. And in fact, we are taking precautions so that the mercury vapor actually does not evaporate. So whenever it is in the motion and layer is formed of vapor, it's always safe. I mean, you can run the telescope throughout night or even. So only thing is that when it is still mercury and your vapor doesn't form, I mean the layer, uh, mercury oxide layer, when it is formed on top of that, it is safe. Yeah.
Manoj Kumar is asking, sir, while observing from Earth, how do we get rid of telluric absorption lines as they are noise without altering the original signal? As the spectral lines are introduced by O2, how do we know whether they are originated in our atmosphere or came from our target?
Yeah, this is very difficult when it comes to the telluric features, and removing them are very difficult. And because it's also it also depends on the amount of oxygen and water vapor we are having in the line of sight. So so typically what we do at observatory is we try to calibrate this telluric feature for a particular site, and given telescope and spectrograph, we try to generate a spectra uh, for that particular observatory, and we make that spectra available to all the observers, so that they subtract this particular feature from their objective spectra. It is, though it is very difficult, and you need very experience to get some intrinsic features from celestial sources for that particular reason.
Our last question, Aaron Gupta is asking, Can we visit Aries if we come to Nainital?
Oh yes, it is. Aries is a public funded institution, and your money is also used to run that institute. So you are always welcome to visit that institute. I mean, you can visit our website, and there is a outreach menu over there. You go through that. We conduct a lot of outreach activities, and in fact, we conduct daily shows. In fact, depending on the manpower, we keep the schedule. And right now, it is every alternate days. We are keeping schedule in the evening, and whenever there is a clear sky and there is availability of manpower, we organize that night shows so that you can see planets through smaller telescopes. But if you are visiting during daytime, in that case also you can visit our institute directly. Of course, giving a call to our office that you want to visit for this and this purpose, and so that there are manpower to attend you and take you around the observatory.
Thank you so much, sir, for answering all the questions and for sharing your knowledge with us. It was an amazing lecture.
Ishita, just I want to take one liberty to ask my question.
Yeah, please.
Okay, I have a very my expertise are not in astrophysics, but I have a question regarding this slide that you are showing right now. There you discussed the relative movement of the galaxies different parts.
Yeah.
My question is, galaxies are not, generally not planar objects, or also they generally not are of spherical objects. They have some distribution of their mass. So in this way, how do you incorporate or how do you identify what kind of galaxy at hand? And how that how the distribution of the different mass or the shape of the galaxy changes such calculations?
Yeah, I think this your question relating to the hidden mass in a galaxy, which is gravity of which is controlling the motions of objects which we see, and for which we are able to obtain spectra. So first of all, there will have to be optical photons. I mean, sources which are emitting optical photons for which the spectra are available. Using spectrum only, we are able to take. We are able to know that with this particular velocity within a galaxy, or with reference to the center of galaxy, that particular object is moving or it is in an orbit, right? So but it so happens that suppose there is some hidden mass from which we are not able to get any light, but that hidden mass is taking part in controlling the motion of that seen mass or seen source. So probably it is reflected in these velocities. So whatever it is plotted over here, so if we study the velocity dispersion and try to apply laws of physics, I mean motion, laws of motion to this galaxy, I mean, this gravitating matter. So if it doesn't follow the known laws, where velocity should be decreasing when you go away from the galaxy center. I mean, it is remaining constant. Rather, velocity dispersion, I would call, of all the objects in a galaxy. If it is remaining, it remains constant. Your dispersion, and it is not decreasing with radius r. So probably we'll say that there is some other mass which is controlling the dispersion of this matter in this galaxy. So this is how we try to infer the hidden mass in and around a galaxy. Yeah, so this is what this is how we study, and you really need low dispersion spectra for such kind of study.
So
But
here, hidden mass is not is the dark matter, or that's a different kind of discussion?
yeah, it could be anything. I mean, but we can only tell from the dispersion of the objects in a galaxy which we see. We can only tell that it is not following the mass which of a galaxy, because seen mass of a galaxy. So there is other unseen mass which is controlling the movement which is coming from the seen sources.
Okay. Thank you. And also, you have also shared the outreach program from Aries. I have one question. In our students already have visited Aries, I think at least one time, one of our group, like 2-3 years ago. So in generally, anybody can, visit anytime, or there are some, like, if you do not take a prior scheduled visit, anybody can attend anytime, or it's always mandatory to take a scheduled visit?
I think it is always good to inform the office that if you are a group of people, let's say a group of 4-5 persons, and if you are having a larger group, it is always advisable to inform the office, because we need to manage at our end. I mean, arrange manpower and arrange the setup to attend to your requirements. But if you are, let's say, if you are with a family, I mean, 4 members, and you suddenly happen to be in the Nainital city, so probably you can directly come to our office and inquire at our reception and say that, look, I have happened to come to your office and want to have a visit. So if it is a working day and during daytime, so people are always there. I mean, they can take you around the observatory. So but if you are in a group, it's always advisable to connect to office.
Generally, what is the best time during the year to?
Yeah, October and November, these 2 months are the best.
Okay.
If you are interested in viewing something in the night, and if you are simply interested to visit the facilities, either at Manora Peak Nainital or at Devasthal Nainital, then any day, any working day, I would say Monday to Friday. And if you happen to come on the weekends, we are going to see if there are people. Our offices are closed on Saturday and Sunday, so that is the limitation.
Thank you.
Thank you, sir, for this lecture and the Q&A session. Moving ahead, we would like to invite Dr. Biswajit Paul for his lecture on the topic X-ray spectroscopy. Dr. Biswajit is an expert in astronomy and astrophysics at Raman Research Institute and also the co-editor of the COSPER publication Advances in Space Research. Sir, we all welcome you.
Hello, am I audible?
Yes, sir.
Okay.
Yes.
Hello, everybody. First of all, let me thank the organizers, especially Dr. Mamata Gulati, for your interest in hearing about X-ray spectroscopy in astronomy. X-ray is probably a less talked about and less familiar branch of astronomy compared to optical and radio astronomy. Everybody is familiar with optical observatories. All of you must have seen pictures of grand radio telescopes and so on. Not many people may have heard of X-ray observatory, and it's out of question to visit an X-ray observatory because X-ray observatories are in space. So with that much, let me get started with my topic. Is my screen visible?
Yes, sir. So actually,
Hello?
there is a small announcement before we proceed with the lecture.
Hello?
Hello? Yes, sir.
Okay. Yeah, so this is what I plan, X-ray astronomical spectroscopy. I would start with telling you various astronomical processes and objects that emit X-rays, and briefly take you through techniques for X-ray astronomical spectroscopy, because to know the subject, you would probably appreciate it better if you also knew some details of how do you actually go about studying this, some details of instruments, and end up with very few, but in my view, some of the most exciting examples of X-ray spectroscopy. So coming to the various processes for various astronomical processes that causes emission of X-rays. By X-rays, let me first clarify what is the wavelength range and energy range. All of you are familiar with X-ray that is done for medical purpose, which is of the order of few 10 kiloelectron volt photons. Photons that are blocked by calcium or other minerals, but not blocked by the muscle material that the muscles are made of. So you get a picture of the bone structure and so on. In astronomy, mostly by X-ray band, we mean the energy band of 3 decades covering from 0.1 kiloelectron volt to 100 kiloelectron volt, or approximately in wavelength range 0.1 to about 100 angstrom. So this is practically around a nanometer. Okay, so the various processes that produce X-rays are you can classify them as thermal emission, like black body radiation, or in a thermal plasma Bremsstrahlung radiation, or non-thermal processes where you have very high energy particles and interaction of these particles with either magnetic field or low energy photons or ions, etc., produce X-rays by various means. While doing X-ray spectroscopy, we are not interested only in the emission. At times, the absorption also becomes absorption phenomena is also of high importance. And absorption could be either atomic processes or sometimes because of electrons moving in strong magnetic field. Okay, so let me take you through one by one of these various emission processes. Black body radiation, as you know, there is this sigma T relation. The higher the temperature of a body is, if it's emitting like a black body, higher is the energy of the peak in the spectrum, or lower is the wavelength in the peak of the spectrum. So as you can see, sun has a temperature of about 6,000 degrees, and its emission peaks at about 6,000 angstrom. If you want X-ray emission, then the emission has to be, if you want X-ray emission from a thermal emitting body, from black body radiation, then the emission has to peak at around 1 nanometer, and then the temperature has to be in the range of about 1 million degree Kelvin to 10 million degree Kelvin. Now, we do not have normal stars of that kind of temperature. As you heard in the previous talk, sun has a temperature of about 6,000 degree Kelvin. Then there are stars with higher temperature of 10,000, 20,000, up to about 40,000 degree Kelvin. So these objects do not emit so much in X-rays from the process of black body radiation. However, some stars produce X-rays from their coronal emission, like even sun. Sun has a surface temperature of 6,000 degrees, but outside the photosphere, there is this thing called solar corona, which has very low density, but very high temperature. That emits in X-rays.
Hello. Sir, you're not audible.
Hello?
Yes, sir. Now it's
Is
fine.
it better now?
Yes, sir.
Should I
Yes.
go back? How far should I go back?
Sir, like 1 or 2 minutes.
Okay. So what I was saying is, sorry about that interruption.
It's okay, sir.
Yeah, a sun-like star or most ordinary stars do not emit much in X-rays, primarily because their surface temperature is only about few thousand to few tens of thousand degree Kelvin. Whereas if you want, or if you are looking at X-ray emission at about kiloelectron volt, then you want the object to have a temperature of about 1 million degrees to 10 million degrees. Okay? So normal stars are not prime X-ray emitting objects. However, stars like Sun and some young stars have a very strong corona, and this corona can have a temperature of million degrees, and you can see bremsstrahlung emission from the stellar corona in X-rays. Even then, stars are not prime objects for normal stars are not prime objects, primarily X-ray emitter. Stars at the end of their evolution of the normal phase, Sun-like star would leave behind a white dwarf, or a more massive star would go through a supernova explosion and leave behind a neutron star. Now, a white dwarf can have a surface temperature which is much higher than a normal star, and a neutron star, especially a young neutron star, can have a temperature of as high as a million degree or several million degree Kelvin. So these kind of objects can have blackbody emission, which itself goes into X-rays. And then there are clusters of galaxies which have very high temperature, and that can also emit in X-rays. Then there are supernova remnants where you can have very high temperature leading to emission in X-rays. So blackbody emission, if you want few keV X-ray emission, then you require a temperature of a few million degrees. The other process which can produce X-rays, and we see commonly, is bremsstrahlung, which is basically a collision between electron and nuclei. The electron has to have a rather high temperature. So when electron is approaching a proton or any other heavy nuclei, depending on the impact parameter, the electron would bend, which is basically acceleration, and that would produce this braking radiation called bremsstrahlung. The direction of the emission and the energy of the emission depends on the impact parameter, that is how closely the electron went past the proton or the nuclei. Now, in a medium, these impact parameters would have a wide range, and therefore you get a continuum emission in bremsstrahlung, and the spectral has a shape like this. The higher the electron temperature is, higher will this energy extend up to. Usually through X-ray spectroscopy itself, we cannot distinguish between black hole and black body type and bremsstrahlung type emission very well. Both of these may come from objects which are at very high temperature. One other process which is very, very common in X-ray astronomy, especially in high energy astrophysics, is called inverse Compton. You are probably familiar with Compton scattering. Compton scattering is where a photon interacts with an electron, presumably a low energy electron or electron at rest, and it loses energy. The inverse of this is also possible if a low energy photon, for example, the cosmic microwave background, which has very low, which is millimeter wave. If a cosmic microwave background or any other low energy photon interacts with an electron at a high temperature or electron with high energy, need not be relativistic. If an electron has a kinetic energy of a few kilo electron volt, and if it interacts with a low energy photon, the photon can gain energy. And that is actually a very common process in high energy astrophysics, whereby photons gain energy, and it is called inverse Compton. Then you have synchrotron emission, where electrons moving in magnetic field, electron moving in magnetic field would gyrate, and this accelerated electron can produce radiation, which is called synchrotron emission. So that is high energy electrons moving in magnetic field. At very high electron energies and high magnetic field, this radiation can go into the X-ray band or even gamma ray band. Then there are various atomic processes that produce X-ray emission, but atomic processes produce X-ray emission which are in narrow band. All the other processes that I talked about so far, the blackbody radiation, the bremsstrahlung radiation, or synchrotron emission, those are usually continuum processes. Whereas when you have an atomic process giving rise to emission, this would be line emission. So, and electron collisions in plasma or high energy radiation into a plasma can cause excitation, right? For example, here you can see an electron interacting with an ion. The electron gets scattered. In that process, it causes excitation in the atom, and that electron would go from lower band to higher energy band, and subsequently it will de-excite, giving rise to a photon emission, which is energy of the photon would be equal to the difference between the energy level of the electron from the excited state to the ground state. So you can see atoms excitation leading to de-excitation and emission of photon, or you can also have fluorescence emission, in which if there is a background X-ray radiation, let's say a source is producing a lot of hard energy, high energy X-rays by inverse Compton process, or if a photon object has very high temperature and it is producing a lot of X-rays. Now these X-rays can get absorbed in the atoms near to the object, and the absorption process is primarily photoelectric absorption, which is in case of X-ray, the photoelectron that will be emitted will come from the K-shell electron. Okay, so what you can have is a K-shell electron could be knocked out, and subsequently an L-shell or an M-shell electron would fill that vacancy, producing an X-ray emission, which is same as the difference between the emission lines. So this is called fluorescence. So de-excitation or fluorescence emission can also produce X-rays, and that is the main diagnostic tool for various elements in objects like supernova remnants, in clusters of galaxies, etc., where the plasma is excited to such a high level that there are no optical transitions. Okay, those objects, only electrons that are left are probably in the innermost layer, and all transitions are between the innermost layers, and therefore most of the emissions are in the most of the atomic transitions are in the X-ray band, and X-ray therefore becomes the main tool for probing these objects. There is also a process called charge exchange, where, for example, a hydrogen atom in an exchange process with another ion can give an electron to the ion, and this electron would be in a higher state, and then it can come back to lower state by emitting an X-ray photon. Okay, so these are processes which we need to probe to understand what is going on in the astrophysical objects. Okay, these are the various processes that gives rise to X-ray emission. I would also mention about X-ray absorption, which is also a way of studying either the abundance of material, their annihilation states, or for example, extremely large high magnetic field around neutron stars. So one very interesting absorption process that we often study is called cyclotron absorption. What you have is sometimes in a neutron star, you can have extremely large magnetic field, and electrons gyrating in that magnetic field would be in discrete orbits. Okay, and photons with an energy very, very close to those discrete orbits have resonance scattering. That is, their scattering cross section is much higher. So now if you have background radiation going through this region where electrons are gyrating around the magnetic field, photons of a certain energy are more likely to be scattered and therefore taken away from their original direction of motion, causing to absorption features in the spectrum. This is called cyclotron absorption, that is scattering of electrons in gyrating in high magnetic field. So these are various emission and absorption processes that are predominant in high energy astrophysics in whole range of objects. And so therefore, let me just quickly tell you various kinds of objects which astronomers study in the X-ray band to understand different features of them that is not available through study of the same objects in the optical or in the radio or infrared band. Okay, X-ray astronomy is a topic that is rather difficult to pursue because X-rays do not come down to the ground. So you have to take our telescopes to above the atmosphere, which means into space. So it's a very expensive affair, and therefore there are very few number of X-ray observatories compared to number of optical observatories or radio observatories. So X-ray band, you primarily target those areas of astrophysics that cannot be pursued by optical or radio band. So objects which emit, for example, stars, I said, they have coronal emission. The high energy electrons in the corona can produce X-ray emission by bremsstrahlung. Primarily the process is bremsstrahlung. Compact stars like a white dwarf or a neutron star can have surface temperature. White dwarf can have few tens of thousands of degrees, and neutron stars can have even million degrees or more than million degrees, and that can emit thermal emission into X-rays. Then you can have supernova remnants, like after a supernova explosion, the center may leave behind or may not leave behind a compact object, but the outflowing material then interacts with the interstellar material, and it causes shocks and heating in the interstellar material, and from there it starts producing X-rays. A supernova remnant can remain X-ray bright for up to few thousand years after the supernova explosion, and after that it slowly dims. Then a very interesting class of objects that emit X-rays are called X-ray binaries, where you have a neutron star or a black hole, but not as an isolated object, a neutron star or a black hole in a binary system. Okay, and when in a binary system, it is able to draw out material or accrete some amount of material from the companion star. This material, when it falls into the deep gravitational potential of the compact star, like the neutron star or the black hole, the infalling material loses its gravitational potential energy, and that, at least part of that, can get converted to high energy radiation. This is a very, very efficient process for converting mass into energy. So if you throw a 1 gram of material into a neutron star, you can extract as much as 10% of its rest mass as energy. Whereas in the process of fusion, that is hydrogen into helium, the conversion of mass into energy is a much smaller fraction. Okay, so accretion is by far the most efficient process for formation of for production of high energy radiation or conversion of mass into energy in astrophysics. I already said that there are processes that produce hot gas, like in supernova explosion. Shocks produce hot gas, but supernovas are not the only process. Anywhere else where you have a high energy stream of particle interacting with low energy but dense material, it can produce shocks, and in the region of shocks there can be heating, and that heating can go up to 1,000,000 degrees, producing X-rays. Then this is a page I will revisit. You have, at the very large scales in the universe, about a few hundred to 1,000 up to even as much as 1,000,000 galaxies forming structures, which are called clusters of galaxies. Now, in a cluster of galaxy, we already know that much of the mass is dark matter, but even the baryonic matter, a large part of it is actually not in the form of stars or galaxies. Okay, a large part of the mass in a large large cluster of galaxies is actually in the form of diffuse gas, a very low density gas of the order of 10 to the power minus 2 to 10 to the power minus 4 atoms per cc, that kind of low density. But this gas, which is trapped in the potential of this cluster of galaxy, has high kinetic energy. Okay, so this is gas and mostly by the process of bremsstrahlung emission. And then you can have, in X-ray binaries, you have neutron star or a black hole accreting material. At a very large scale, you can have supermassive black holes with mass in the range of million solar masses to about 10 billion solar masses. Like at the center of our galaxy, there is a black hole with a mass of about 4 million solar masses. So these very massive black holes can also accrete gas from its surrounding, and that accreted gas can also get converted to high energy radiation, again by the process of accretion and loss of gravitational potential of the accreted material. These are called active galactic nuclei. These are also very interesting objects. Then there are objects or phenomena called gamma ray bursts. Every now and then, roughly once a day, there is a gamma ray burst somewhere in the sky, randomly distributed, isotopically distributed at cosmological distances. Gamma ray burst, which is a short flash of X-ray and gamma ray. The origin of these, there are two potential origins. One is a merging neutron star. Two neutron stars in a binary system, after they radiate away some energy by gravitational wave radiation, can eventually merge to produce gamma rays, or certain kind of supernova can produce gamma ray bursts. That's what we know of now, but this is not a subject which is completely closed. There are a lot of new investigations going on. Maybe we'll know more about this in future. So these are various astrophysical objects, a whole range of objects that emit X-rays. And I already told you about a whole range of astrophysical processes by which X-rays can be produced. And therefore, there is large interest in studying these objects with various instruments. And as it goes with all branches of astronomy, spectroscopy is the branch that tells us most about the processes. Okay, so X-ray spectroscopy, therefore, is of very high importance in. Spectroscopy is of very high importance in X-ray astronomy as well. So before showing you any results, I would quickly take you through. I'd like to quickly take you through a few slides showing how these measurements are actually possible. How does one do X-ray spectroscopy? Okay, by spectroscopy, we generally mean our ability to measure the wavelength or energy accurately. Okay, there is one other aspect of spectroscopy, which is we also need to know, especially if you are measuring the continuum in a source, the quantum efficiency correctly. Okay, for example, if there is a telescope, then the telescope throughput as a function of wavelength, and after the radiation falls onto my imaging instrument, the quantum efficiency of the instrument across the entire energy band. Okay, all of these needs to be known accurately to be able to do continuum spectroscopy. Whereas for line spectroscopy, where you are more interested in measuring the line energy or energy of a photon very, very accurately, it's the energy resolution that is of importance. So let me take you through quickly a few slides where I show various processes by which X-rays interact with material, and subsequently they are detected. And when it is detected, how accurately and by what process we are able to measure their energy, which allows us to do the spectroscopy. So here are images of few objects that shows. Sorry, I need to exit and come back. Here are few representative images of various types of objects in X-ray band that emit. There are strong X-ray emitter. Here is image of a supernova remnant. This is a famous object called Cassiopeia A. This is a supernova that exploded, I think, about 300 years ago. It left behind a very tiny, you can see that white drop at the spot at the center. That is a neutron star. So this supernova left behind a neutron star, and the outflowing material, which is primarily the material from the star, outer shells of the star, which has exploded. And this outflowing material is interacting with interstellar material, whatever was there surrounding the star. It's interacting, it's producing shocks, and at the shock, gas is heated. The heated gas then produces X-rays. And inside that outflowing shock region, there is X-ray heated gas, which is ejected from the supernova remnant, which also produces X-rays. And these X-rays can have two origins. One is it could be bremsstrahlung because of the high energy electrons, and it could also be the atomic emissions from the outflowing material. So as you know, in a supernova, you have production of various elements, like elements up to iron is produced in the star before the supernova explosion. And when the iron core cannot produce energy anymore by nuclear fusion, because iron has maximum binding energy, after that, when the supernova explodes, during the explosion process itself, other higher jet elements are
Sir?
Thrown out into the interstellar material in the supernova explosion process. So these are thrown out into the interstellar elements other than hydrogen and helium, right? Hydrogen and helium. Whereas hello? Is audio cut? Good?
Yes, it's fine. So actually, internet connection was not stable earlier, so like voice cracked a bit.
Achha, okay. Now it's okay?
Yes.
Yeah. So everything around us, the Earth, all of us are made of elements that are synthesized inside stars, or elements heavier than iron was synthesized during the supernova explosion. So how all of that is thrown out to become available for formation of planets and subsequently everything else is very beautifully captured in this kind of an X-ray image, where you can see the blue light shows the shock fronts where the outflowing material is interacting with the interstellar material, and all the other colors, lighter colors, that is green, yellow, red, etc., are representative of various elements which are being thrown out into the interstellar material. This is image of a supernova remnant. This is these are not images; these are artist sketches of an X-ray binary. X-ray binaries are the most brightest X-ray objects in the sky on the binary system. Accreting material from Earth, and the neutron star is this white dot at the center, which is accreting some material from the companion star, and the material, because of its angular momentum conservation, cannot fall directly. It forms a disk, and through this disk, it goes onto the neutron star, and where the material is heated and produces X's. Okay. So as you can see, for per unit mass of material, the energy loss will be gm by r when it falls on the surface of a neutron star. Now, a neutron star has a radius of only about 10 kilometers, that is 10 to the power 6 centimeter. G has a unit of 10 minus 8, whereas mass, which is mass of a neutron star here, is about 10 to the power 33, few times 10 to the power 33 grams, right? So this is a large number, about 10 to 20. So if you throw 1 gram of material, you are able to extract about 10 to the power 20 ergs of energy, which is about 10% of the rest mass of the material that is being thrown in. That is why it's a very, very efficient process, accretion. In another type of X-ray binary, you have a neutron star, which is at the center of this diffuse object on the right-hand side. And on the left-hand side, you have a normal star, but a high mass star, like 10 solar mass. Heavy stars, they have very high energy radiation, like ultraviolet radiation, strong ultraviolet wave continuously. There is very strong. This kind of a binary system can accrete material, can produce X-rays. Okay, so this, which is a compact object, accretes material from a companion, producing a large amount of X-rays. It's a very efficient process for conversion of mass to energy. And by spectroscopic study of these objects, we learn very, very interesting things. I would cover some of that at the end. If you go to objects at much larger scale, like at the center of our galaxy or center of most other massive galaxies, there is a black hole. This black hole can have mass in the range of a few million solar masses up to about 10 billion solar masses. Now, such a massive object can draw in material from the surroundings, again, most often through an accretion disk. And the infalling material again can lose energy and produce a copious amount of X-rays. These kind of galactic nuclei can be, very, very bright. Quite often, they're called quasars. Quite often, such objects can grossly outshine the entire galaxy. The central 1 billion mass object can outshine the entire galaxy by very large factors. So that quite often, rest of the galaxy may not even be visible. Okay, so we use X-rays emitted from these central objects, and by their spectroscopy, study the objects themselves. Sometimes study how do they interact with the environment, or how do they interact with the intervening material between the object and us, to understand more about either the reprocessing material in the environment or the intervening region. Okay, so I would talk about a little bit about those as well. Here is image of a cluster of galaxy. On the right hand side is an optical image. Okay, what you see in the right hand side image, there are a few dots. Those dots represent the galaxies. At the center, there is a bigger galaxy, and surrounding it, there are hundreds of smaller galaxies. Okay, in optical, you primarily see the starlight. And when you see a galaxy image, it's basically a collection of the radiation from all the stars in it. So right hand side image is primarily the starlight image. The same object, when you see in X-rays, you do not see these individual dots, okay, because the stars are not, very strong X-ray emitters. Instead, the same region of the sky, if you look at it in X-rays, what you see is a large-scale diffuse emission. Okay, this diffuse emission comes from the hot gas, which is in the intervening region between the galaxies. Okay, this is the intercluster material emitting emitting X-rays. Now, it so happens that in a cluster of galaxy, actually, even if you talk about the baryonic matter, a large fraction of the baryonic matter has not formed, has not been captured in stars and galaxies. Okay, large part of it is diffuse material in the cluster, and in the cluster's gravitational potential. So when they collapsed into this cluster, half of it is retained as kinetic energy of the particles. Okay, and that is why the particles, the electrons, have rather high energy of few kilo electron volt, and they produce X-rays, large amount of X-rays by bremsstrahlung process. Okay, so actually our visibility of a large fraction of the baryonic material is only about 4% of the energy density of the universe. A large fraction of that matter can actually be seen only in X-ray. Okay, so and therefore X-ray spectroscopy tells us the abundance of this material, tells us the velocities of this material in this gravitational potential, and so on. And that is where lies the importance of X-ray spectroscopy. Okay, so coming to actually doing X-ray spectroscopy, as I said earlier, we are protected from cosmic X-ray radiation, cosmic ray itself by the atmosphere. Okay, otherwise cosmic ray radiation, X-ray radiation, gamma ray radiation, etc. are very harmful for all living creatures. So we are protected by the atmosphere. At the same time, this also makes it difficult to study the universe in those wavelengths band which is absorbed by the atmosphere. So actually atmosphere is transparent in the optical band, which is just a fraction of a decade, like going from about 5,000 angstrom to 3,000 angstrom to 10,000 angstrom. And in the infrared band, it is partially transparent, and it is quite transparent in the radio band of a few centimeter to about 10 meter. Everywhere else, the atmosphere is opaque. Okay, so in X-ray gamma ray band and in the far infrared band, we essentially have to take our instrument to space to do any studies. So that is why X-ray astronomy is more expensive, more difficult to do, and it had to wait till advent of space technology. X-ray astronomy practically is a subject that started in early 70s. Okay, so since the topic is X-ray spectroscopy, I would like you to know, when you want to do spectroscopy, as I said, we need to know two things. One is quantum efficiency of our entire system at over the entire energy band that we are covering, and the other thing is our ability to measure the energy of the incoming X-ray photon accurately. Okay, now X-ray detectors are of various kinds, and in various kinds of detectors, different principles apply. So I will go from higher energy to lower energy in some sense. So the high energy detectors, most common type of high energy X-ray detectors are the scintillators. In scintillators, what you have is a high energy photon like 50 kiloelectron volt or 100 kiloelectron volt photon can get absorbed in the scintillating material. It will be absorbed by photoelectric process, and after absorption, an electron will be emitted, which will carry most of the energy of the incoming photon. Okay, this electron will cause ionization in the material, that is electron-ion pairs, and those secondary electrons would then produce what is called scintillating light. Okay, this light comes out through the material and could be captured, or at least a part of the light could be captured by a photomultiplier. And the signal of the photomultiplier for one incident X-ray photon would be a measure of the amplitude of the photomultiplier signal would be a measure of the energy of the incident photon. Now, as you can see, in this kind of a setup, depending on where the incoming photon has fallen and what fraction of the optical light that is emitted, scintillated light that is emitted, is reflected back and eventually entered the photomultiplier tube, and what is the quantum efficiency of the photomultiplier, etc. There are several uncertain factors. All of that together makes the scintillator detectors rather unattractive for X-ray spectroscopy. However, at energy above about 50 kiloelectron volt, we have no other device. Scintillators are the prime devices for X-ray measurement. Nowadays, there are new devices called cadmium zinc telluride, which are some sort of semiconductors, so which gives slightly better energy resolution. The next type of device is proportional counter, where you have an X-ray photon absorbed in a gaseous medium by photoelectric absorption. The photoelectron then produces a small ionization track, that is large number of electrons are produced, of the order of few hundred to few thousand per X-ray photon. These electrons are then accelerated towards a narrow anode wire by applying some high voltage onto the anode wire. And very close to the anode wire, the electron goes through multiplication, because as the electron is approaching the anode, it gains energy, and at every step, it can, in subsequent scattering with other atoms in the medium, it can produce more and more number of electrons. Okay, so a single electron or a single X-ray photon incident can produce a large number of electrons eventually onto the anode, producing a negative pulse. And amplitude of that pulse is a measure of the energy of the incident photon. Okay, so proportional counters therefore give energy resolution of the order of 10%. Scintillators give about 25 to 50%. Proportional counters are the next big thing for the X-ray spectroscopy. A somewhat modified proportional counter are this gas scintillating proportional counter, in which the primary electrons which are produced are accelerated in a parallel electric field to another surface, and these accelerated electrons go through a certain gaseous medium where it, in interaction with the medium, it produces a scintillating light. Okay, then the light is detected with a photomultiplier tube, and the multiplication process here is very effective, giving rise to a more accurate measurement of the energy resolution. So gas scintillating proportional counters typically give about 5% energy resolution. So we are improving in energy resolution, going from scintillators about 25%, proportional counters about 10%, then gas scintillating proportional counters about 5%. Then comes the CCDs, charge coupled devices. Charge coupled devices are pretty similar to what you use in your camera, digital cameras. Okay, except that in when a charge coupled device is used in optical, like in an optical telescope as well, the signal in any pixel represents the number of optical photons fallen onto that. Whereas in X-ray band, we make sure that only one X-ray photon has fallen to a pixel, definitely no more than one photon has fallen onto a pixel. And there, the amplitude of the pulse from a pixel represents the energy of the X-ray photon. In case of an optical CCD, it represents the number of optical photons. In case of an X-ray CCD, it represents the energy of a single photon. Okay, therefore, the X-ray CCDs are a spectroscopic device, and they have quite good energy resolution of about 2%. Okay, so you can know the energy of a single photon with an accuracy of about 2%. The best X-ray X-ray spectroscopic devices are the so-called microcalorimeters. In a microcalorimeter, what you have is you have an X-ray photon falling onto a tiny metallic absorber. Okay, make sure that the absorber is at a very small in size, so that a single X-ray photon absorption, a single photon of energy of few kilooelectron volt, can cause a tiny but definite increase in the temperature. Okay, and this object is kept at a very low temperature of less than about 100 millikelvin. On which even a small change in temperature can be measured very accurately. So whenever an X-ray is incident, the temperature will increase by a few microkelvin, and then over a few milliseconds it will disperse. The heat will be taken away to the heat sink, and thereby giving very, very accurate measurement of the energy of the incident photon. In microcalorimeters, one can get better than 1%, better than 0.1% energy resolution. Okay, microcalorimeters are the best devices so far. And once you have 1 in 1,000 kind of energy resolution, you can actually, if you are looking at objects which have line emission or line absorption, you can measure the velocities down to few tens of kilometers. And that is very, very important in studying, for example, dynamics in star clusters and so on. Okay. However, there has not been a successful X-ray astronomy mission with a microcalorimeter. The last time it was attempted, the instrument worked for a few days. There was observation of only one object, and after that, the instrument had a malfunction. The satellite had a malfunction, and the next mission will probably be launched in less than 2 years from Japan. That's a Japan-US collaboration. These are all non-dispersive devices. If you take dispersive devices, then one can use grating. And there are two X-ray observatories, Chandra X-ray Observatory and XMM Newton, in which X-ray grating devices were used. Either in grating or in Bragg reflection, what you do is you cause the incident photons to disperse and measure the dispersed photon using a linear device. Okay, maybe a array of CCDs. Okay, and thereby measure energy resolution. Thereby measure do spectroscopy, and in grating you get energy resolution which is somewhere in between the CCDs and microcalorimeter. Black reflection is another way of doing X-ray spectroscopy, but it's a very inefficient method. It is usually not used in astronomy because X-ray astronomy, as I said, it's a very expensive endeavor. You have to take your instrument to space and so on and so forth. So black crystal, which works only at one angle at a time, is therefore not a very suitable device for doing astronomy. Okay, so now we have talked about the physical processes that produce X-rays, the objects in which X-ray production takes place, the ways by which we can measure the energy of X-ray photons. Okay, I would then come to show you few examples, not too many, few examples how we actually measure X-ray spectrum of sources and then conclude something about these objects. Okay, however, it's not so straightforward because quite often you would be looking at an object in which there are multiple physical processes happening simultaneously, and there are multiple emission components in the same objects. Okay, so the question comes down to, can we disentangle these multiple processes by doing X-ray spectroscopy? Here I'll show you one example of that. You have a neutron star, which is this ball at the center. It has high magnetic field, about 10 to the power 12 Gauss or so. It is accreting material from a companion star through this accretion disk. Okay, now this disk material, when it encounters the strong magnetic field of the neutron star, it's ionized material, so it cannot go perpendicular to the magnetic field lines. It will follow the magnetic field lines and fall onto the polar region. From the polar region, you have X-ray emission. That is usually a power law type emission because emission here is produced by inverse Compton processes. Okay, inverse Compton process is what I discussed in the very beginning. You can have small thermal emission from surface of the neutron star. Those thermal low energy photons will go through inverse Compton scattering in the electrons which are falling from the accretion disk onto the magnetic poles. Okay, so if we talk about the X-ray emission, the primary emission is a power law type, has a power law type shape. Okay, which is this straight line. This is produced by inverse Compton scattering of the low energy photons by the high energy electrons falling onto the polar cap of the neutron star. Now these infalling electrons have a higher energy range. Let us say it is of the 20 of the order of 20 kiloelectron volt or 30 kiloelectron volt. Then of course those electrons cannot Compton upscatter photons to much higher energies, and that's why you have a cutoff in the spectrum. It's called usually it has an exponential cutoff. Now these X-rays are not only reaching us directly. Some of these X-rays may also get reprocessed in the surrounding material. Okay, it could be the surface of the companion star, it could be the accretion disk. So when these X-rays interact with the accretion disk, it would cause heating of the disk material, and that heated material can produce low energy X-rays. Okay, this large bump shown on the low energy part, this is the heated emission from the inner accretion disk. Okay, then the surrounding material, for example, the stellar wind, the circumbinary material, or anything around it, okay, would also receive these X-rays, and there could be fluorescence emission from the material in the surrounding matter. For example, iron has quite large abundance, and iron also has high yield for fluorescence emission. So you may as well have some iron lines produced by fluorescence of which is induced by the X-rays coming out from the compact star, and the fluorescence material is in the wind of the companion star. Okay, so fluorescence will produce like 6.4 kiloelectron volt iron K lines and this around 1 kV iron L lines. Okay, and then you have this black body emission, reprocessed emission. So as you can see, this spectrum is quite complicated in nature. It has multiple components in it. And in the higher energy part, very high energy part, like around 30 kiloelectron volt in this particular spectrum of this source, there also seems to be another absorption feature in the falling part. Okay, that is the cyclotron absorption line. Fine. So now, what is shown in the right hand side is actually not what is observed. Okay, what is shown in the left-hand side is observed for various reasons, because you can see this energy spectrum covers from 0.1 to 100 kiloelectron volt. And as I said before, you have different techniques for doing X-ray spectroscopy in different energy bands. In the high energy part, like above 20, 30 kiloelectron volt, you use scintillator detectors. Okay, so if you see the left-hand side plot is the actual observed spectrum. The highest energy part is from scintillator detector. The medium energy part is from gas scintillating proportional counter detector, and at the lower energy part, you have two X-ray telescopes along with different low energy X-ray detectors. Okay, so this whole spectrum that is obtained for a given source is actually obtained by different instruments, having different effective area, having different quantum efficiency, having different spectral resolution. Okay, all of that producing this observed spectra. Challenge is, can we derive the intrinsic spectrum of this source from this observed spectrum by knowing the characteristics of our instrument as well as we can. Okay, so let me quickly tell you how do we actually do it. It's not the most satisfactory process, but this is what is currently available to us. First thing you need to know is the response matrix of your instrument. That is, for X-ray photons falling with a given energy E, for X-ray photons falling with a given energy E, in your instrument, how those photons will be distributed. Okay, if the instrument has poor resolution, then photons will be distributed across a large number of channels. If the instrument has very high resolution, then it will be distributed in a narrow channel. If the instrument has different quantum efficiency across its energy band, that also has to be absorbed in this term R. Okay, so this term R, where E is the incident energy of the incident photon, and I is the let us say pulse amplitude, and amplitude of the measured pulse. Then how I and E are distributed is the so-called response matrix of your instrument. We need to know this very accurately. Okay, what we are trying to derive is the source function f as a function of E. What is the distribution of photons of the source that we are studying? What is the distribution of the incident photons in the source? Okay, this is the spectrum. F as a function of E is what we are trying to determine. What we have observed is this C as a function of I. Okay, this is the observed spectrum. Ri is the response of the instrument. Fe is what we are trying to determine. Okay, now this is not invertible. So instead, what we do is that, given the nature of our source, we assume some shape of the spectrum of the source, which in the case that I showed you has a Paolo component. Paolo component has a cutoff. There are emission lines. There is a black body component. So we put all of that in the model, multiply it by the response matrix, compare that with the observed spectrum. Okay, so Ci is the calculated spectrum for a given source model, and CPI is the observed spectrum. We look at the difference between these two, divide by the error for measurement in each of the energy bands. Okay, and that gives us what is called chi-square. Then we keep varying the source model parameters to reduce or minimize this chi-square. Okay, and when you have minimized chi-square, and if the reduced chi-square is acceptable, we can say that the model parameters which have been taken to obtain this fit are some viable, is at least one acceptable set of parameters for the source. We can never say that this is the observed parameter. This is a set of acceptable parameters. And then one has to worry about how good was the fit and the parameters that we have determined what is the confidence level of that, and so on and so forth. So X-ray astronomy actually does involve a whole lot of intermediate process also. What you observe is not what is there in the source. You have to sort of derive the confidence level of what is there in the source. Okay, I will then show you a few interesting examples of various kinds of X-ray spectroscopy results, not too many, just for you to go back with some picture in mind that this is what happens in X-ray astronomy. One interesting thing is a phenomena of Compton recoil of X-ray photons. Okay, an X-ray photon from a source may reach us directly, or it may, if the source is in a very dense environment, then some of the X-ray photons may reach us after one scattering from an electron. Okay, and if the scattering is from an electron which is on the other side of the source, then it's a 180 degrees scattering, right? It's the photon is turned back by 360 degrees, and in that case there could be a significant energy loss. Okay, if you can measure that energy loss, then you would have detected Compton recoil of X-ray photons. This is a very interesting phenomena, but in whole of X-ray astronomy, there is only one source where this has been measured with high confidence. That is an X-ray binary system, a high mass X-ray binary system, where you have very strong wind outflow from the companion star, and some of that wind is captured by the neutron star. The neutron star produces X-rays. Some of these X-rays are reprocessed by the wind itself. Most of the reprocessing photons are fluorescence photons from iron line. Okay, so in the spectrum of this source, we see a very strong iron line feature. However, even the iron fluorescence X-rays need not necessarily be emitted and reach us directly. Okay, some of the iron emission lines would get Compton scattered in this dense interstellar wind or dense circumstellar wind. And if the scattering is from an electron on the backward, that is, it's a complete 360-degree reflection, then we could see a reflection hump. Okay, so I would show you the spectrum now. This continuum line is the X-ray emission from this source. There is a step here. You ignore that step, that is absorption in iron. You concentrate this large emission line, where my cursor is. Okay, this is the 6.4 kiloelectron volt line. On the left-hand side of it, you can see a step, small step. This continuum emission has caused the wind around the high mass companion star to produce these iron emission lines. This is 6.4 kiloelectron volt iron K alpha line, and this is 7.1 kiloelectron volt iron K beta line. And some of these iron fluorescence photons have reached us directly. Some have reached us after a scattering in the electron. Okay, and that Compton scattering has caused a loss of energy by about 150 electron volt, and that is what has produced a strong left side wing. Okay, this is a Compton recoil. This is called Compton recoil, and this is a very interesting feature. However, there has been only one object in astronomy in which this has been seen. Okay. That is one interesting example of X-ray spectroscopy. Another interesting example I will show is the phenomena of gravitational redshift. Okay. Now, if you have a neutron star or a black hole, as shown in this picture on the right-hand side, this is artist sketch. This compact star is emitting X-rays. The infalling material is losing gravitational potential energy, and as it is going inward, it's getting heated. So there is large amount of X-rays produced from the accretion disk. Now, just like our sun, which has a very strong high energy corona, sometimes this accretion disk also has a high energy corona surrounding it, okay, which produces high energy X-rays, like solar corona produces high energy X-rays. Those high energy X-rays sometimes would get reprocessed in the accretion disk. Okay, by reprocessing, I mean it could produce fluorescence line. Okay, so similar to the spectrum in the previous figure, you can have 6.4 kiloelectron volt line produced by reprocessing of X-rays in the accretion disk itself. Okay, however, now the iron atoms which are producing this iron line are moving around the compact star, moving around the neutron star or the black hole at very high velocity. Okay, it's fraction of a velocity of light. So the radiation which is coming out from there, you expect the following phenomena on it. If the atoms were, if the original line emission is at 6.4 kiloelectron volt, you would expect, simply because of motion of the particles, some of them would show a red-shifted component, some of them would show a blue-shifted component. Okay, so therefore, instead of a narrow line, because of just Newtonian effect, you expect to see a broadening of the line and two sharp edges. Okay, that is the top figure. Because of special relativity, because these particles are moving at relativistic effect, you expect to see transverse Doppler shift, which means the blue shifted component will get enhanced, and this whole pattern would shift to slightly lower energy band. Then, most importantly, this radiation is coming from a very strong gravitational field of the black hole or the neutron star. This radiation is coming from few times the Schwarzschild radius of the black hole. Okay, therefore, this radiation, when it comes out, it also would lose gravitational potential energy. That's called gravitational redshift, and as a result, you expect this whole pattern to be shifted to the left because of general relativity. That is gravitational redshift. And this is what you would expect, but your instrument always has a finite resolution. Therefore, instead of seeing this, you would see slightly diffused pattern like what is shown in the bottom panel. This is what is expected from the spectrum of this kind of a source. And this is what has been observed. Okay, not one, many sources. There is a 6.4 kiloelectron volt line, but you don't see the line at 6.4 kiloelectron volt. You see it slightly shifted, and then there is a strong low energy wing to it, which presumably is the signature of gravitational redshift. Okay. Earlier, I showed you a spectacular image taken with an X-ray imaging spectroscopy satellite called Chandra X-ray Observatory of supernova remnants. Okay, where there is a central bright object, a neutron star, and the outflowing material had interacted with the interstellar material, producing X-rays of different energies. Some of it is thermal energy, which is a continuum, and some of it would be line energies, which are coming from various atomic species in the diffuse gas. So if you look at the spectrum of a supernova remnant, in this case, it is spectrum of the same supernova remnant, Cassiopeia A, you see an underlying continuum emission and then several line emissions. The observatory is, which allows for both optical imaging and both X-ray imaging and X-ray spectroscopy. What you can then do is also make images in narrow energy bands in which the line emissions dominate, like silicon, sulfur, calcium, and so on. Okay, and if you do that, this is what you see. The same object, its images in different line energy bands show how the various atomic nuclei are thrown out into the interstellar medium in the supernova explosion process. Obviously, it is not symmetric. Okay, these are images for iron emission line, silicon emission line, sulfur emission line, and calcium, and so on. Same thing is possible for a cluster of galaxy. In a cluster of galaxy, you have hot gas. This gas would have been enriched since the formation of the cluster by supernovas that have gone into the individual galaxies. Okay, some of the supernova ejecta would have thrown away some material into the intergalactic material, thereby enriching the intergalactic material. And now that the intergalactic material is hot, most of these elements are very highly ionized. Okay, and once material is very highly ionized, you do not see optical lines or other lines anymore. Most of the transitions that would take place, if at all, would be involving the K shell electrons. Okay, and therefore you see a lot of low energy electrons. In case of iron, you may see L shell electrons as well. So if you see the spectrum of this kind of a cluster of galaxy, which where the temperature is not so high that all atoms are completely ionized, but you can still see the inner layer transitions of various elements, and thereby you can study the abundance of material in them. If you have very high resolution spectroscopy, you can even measure the flow of the gas. Okay, and in a cluster of galaxy, flow of the gas would indicate how quickly the center of the cluster is cooling down. Unfortunately, that would require the next generation X-ray telescopes, like the one that is planned between NASA and JAXA for a launch in a couple of years' time. This would be achieved with what is called microcalorimeter spectroscopy. So I hope you got a overall view of how X-ray spectroscopy is done, what are the processes involved in X-ray spectroscopy, and when you do X-ray spectroscopy, what kind of science we learn from it. And I would stop here and take questions if you have any.
Thank you so much, sir, for delivering this lecture and giving your time. And sir, here are a few questions from audience. So first question is by Bandhan Goyal. He has asked, please tell the fundamental physical mechanism behind synchrotron radiation.
Synchrotron radiation is you have a high energy particle moving in a magnetic field. Okay, so if an electron is moving in a magnetic field, then the electron gyrates in the magnetic field, right? And when it is gyration means it's acceleration, right? An accelerated charged particle would radiate, and that's what we see. It's any charged particle moving in magnetic field would have a curved radiation, motion in a curved path, and that leads to radiation. Any accelerated charged particle would radiate. That's what happens in synchrotron emission.
Okay, sir. Sir, and then second question is by Spandan Malik. He has asked, provided nebula is a cluster of gas and dust, what gives nebula an impetus to concentrate matter enough to kickstart formation of a star?
Can you please repeat that?
Yes, sure, sir. Provided nebula is a cluster of gas and dust, what gives nebula an impetus to concentrate matter enough to kickstart formation of a star?
If I understand it correctly, nebula, there are various types. Okay, one is, for example, a star when it is throwing out its outer layer of material. That outer material, when it then the thrown out the ejecta, when it interacts with interstellar medium, it causes heating and so on. So that leads to very interesting emission patterns from them and very beautiful images. If the ejecta of an outflowing star interacts with interstellar medium by causing further pushing of the material and causing density inhomogeneities, then density inhomogeneity can lead to star formation. So that probably happens by very high mass stars in a molecular cloud. Once some stars are formed, these stars would cause further density inhomogeneity by the outflowing material from the star itself, or when a star goes through a supernova remnant, then also it will cause some ejecta to move into the interstellar medium, thereby causing further density enhancement. And those density enhancements are the ones which causes further star formation. I must admit that I'm not an expert in this area. Probably Dr. Brijesh Kumar, if he's still in the audience, he can answer that.
Okay, sir. Sir, there is one more question from Spandan, and he's asking, like, since we have discovered discovered the black hole Sagittarius A at the center of our galaxy, do scientists think that is a bigger amount of concern than the ultimate demise of Earth due to the astronomical death of the sun?
No, I don't think having a black hole at the center. Okay, first of all, let me correct the statement that we have discovered a black hole at the center. What is known, it's most likely that there is a black hole because most galaxies have a black hole at the center. We have evidence of a black hole because it's a black hole which is accreting material from the inner part of the galaxy, which can power such huge radiation that we see. Okay, so as of now, it's quite well understood that there are black holes at the center of every galaxy. The black hole at our galaxy, at the center of our galaxy, is not active right now. It's not a strong emitter. That is also known in several other galaxies, that there may be black hole but dormant. What has been discovered in our galaxy, and for which this year's half Nobel Prize was awarded, is measurement of orbits of stars in the very central part. Okay, but even then, the closest approach of any of these stars is several hundred times the spatial radius, I think, of the presumed central mass. So what has been measured is a massive central object, mass of about, I don't know exactly, it's probably about 3 million solar masses. So a 3 million solar mass concentrated object at the center of the galaxy has been, let us say, established beyond any doubt, which is most likely to be a black hole, but this is not a direct evidence of a black hole. That is one thing. Second thing is any impact of such a central object to sun or us is no different from whether irrespective of what the object is, whether it is a black hole of that mass or just a star cluster of that mass or a diffuse mass of that size. That doesn't have any different dynamical effect on us than a black hole. We are affected by the entire mass that lies between us and the sphere of this radius, between us and the galactic center. Okay, so irrespective of what the nature of that mass is, the gravitational effect is same. So the evolution of sun will not be impacted by what is the nature of the central object in our galaxy, and neither will be Earth's evolution. So Earth and sun will not be impacted in any way whether the central object is a black hole or not. And in case of our galaxy, it is just mere 4 million, where the galactic mass is probably about 10 billion solar masses. Okay, so the galactic central object is actually dynamically, mass-wise, is not significant in case of our galaxy.
Okay, thank you, sir. So one more question, like, Which and when was the gamma ray burst noted nearest to the Earth?
Most gamma ray bursts, actually, what happens is it is rather difficult to know the distance. Gamma ray bursts were known from, I think, late 70s, early 80s. First time when one could definitely measure the distance of a gamma ray burst source was late 90s with this observatory called Bepo-Sachs, which not only detected a gamma ray burst, also detected an X-ray afterglow. That is, from the location of the gamma ray burst, there was an X-ray emission as well, and X-ray, it having an X-ray telescope could narrow down the part of the sky from which gamma ray burst has come. Normally gamma ray burst, because they occur from any part of the sky, the instruments that you use for detecting gamma ray burst do not have angular resolution to tell you exactly where the burst has come from. Okay, this Bepo-Sachs telescope was the first one which could pinpoint the part of the sky from which it has come, and subsequent very quick optical follow-ups and so on could find that there was a supernova explosion, and even the distance to the galaxy was measured and so on. So that measurement happened in late 90s, the first distance measurement to a gamma ray burst, and subsequently this has been done with much better with other telescopes which are flown, like in particular the Swift gamma ray burst telescope. But these are all extragalactic sources.
Okay.
So distance of few megaparsec.
Okay, sir. And the next question is by Bandhan Goyal. His question is, what is the material of the mirror in an X-ray telescope?
Oh, that's a very interesting question. In a radio telescope or in an optical telescope, the light is reflected normally from the surface of the telescope. However, that technique does not work in X-ray. X-rays would not get normally reflected. X-rays will get absorbed in any material. And therefore, in X-rays, we cannot make a telescope by a reflection, normal reflection. Okay, in X-rays, what we do is we use what is called grazing incidence reflection. Like, if you throw a piece of stone on a sea surface, on a water surface, at a very grazing angle, the stone would bounce, right? Something similar happens when you shine a metal surface with X-rays at a very small angle, almost along the surface, less than 1 degree, the X-ray can get reflected. But this reflection would occur only if the surface of that material has high atomic number. So X-ray telescopes are made by what is called grazing reflection. And the material used is usually either gold or tungsten and so on, very high atomic mass material. Hello, is that clear?
Yes, sir. Sir, next question would be, like, how to differentiate between a direct light from a faraway AGN compared to the one of the nearby AGN that first circles around the center before shooting towards us, both coming from the same direction. Bandhan has framed the
Please
question.
repeat the question.
Okay, sir. How to differentiate between a direct light from a faraway AGN compared to the one of the nearby AGN that first circles around the center before shooting towards us. Both are coming from the same direction.
I don't get the circling around part of the question. If the first question only means how do you know the distance to an AGN?
Yes, sir.
If the question is how do you know the distance to an AGN, that would be known spectroscopically. If the associated galaxy is also observable, like in case of quasars, you see the central object only, and the galactic emission is
Hello. Hello, sir.
I guess सर का नेट इशू है. We'll wait for a couple of minutes.
Yeah. Network issue. Bandhan, are you here? You asked that question, right?
Yeah, Bandhan Bhaiya is with us.
Okay, Bandhan. Yeah.
Yeah. Hello, am I audible?
Yes, yes. So you can you may ask your question whenever sir join.
Sure.
Meanwhile, Pramit, what you can do is share your screen and just tell the audience about the
Okay,
break
okay.
that we have, lunch break.
Okay. So like we have break at from 12:45 to 1:45, and as soon as we are over with questions, you can have your lunch, and you can either leave this meeting or stay joined in this meeting, but you just have to mute your mic and turn off your video, and then you can again attend the lecture at 1:45. You can either leave this meeting or you can stay connected with this Zoom meeting, and the link would be same. You just have to join the same link after the break. And after break, we would have lecture on radio spectroscopy by Dr. Nisam Kanekar, and then it will be from 1:45 till 3, and then we would have panel discussion from 3 to 4. So, like, if anyone has any doubt regarding the schedule, they can ask in the chat.
Uh, can I add something over here?
Yes,
Yes,
ma'am.
ma'am.
Yeah.
Yes, ma'am.
Okay.
Sure.
So Dr. Bishwaji just now called. So he had some power issues at his end. So he has requested that if there are any important questions, he can take those questions during the panel discussion.
Okay.
And yeah, so we can wind up the first session, pre-lunch session, and meet after the lunch. Before we end, I would like to thanks both the speakers from our side, but I guess both of them are not here. So let's keep the vote of thanks for the end. And we'll see you guys after the lunch. Do try to join 5 minutes early so that we can keep up on the time of the schedule. And yeah, that's all from my side. If you want to add something, you can add.
Okay, thank you, ma'am.
Yeah.
Hello?
So,
Yes, sir.
yes, sir.
Okay, just one thing. When you start the next session, probably if you have a like 2-3 slides about our society and everything,
Okay.
that would be great to share with all the participants. Maybe for 2-3 minutes, someone just prepare and talk about it for like 2-3 minutes or 5 minutes before you start the next session, just for
Okay,
the
sure, sir.
advertisement. Yeah.
Okay, sure, sir.
Yeah.
So, like, now everyone is requested to have their lunch, and before that, I just want to inform that whatever questions you have during the lecture, you are requested to ask those questions to the participant named task moderators. You may see in the participants list task moderators, and you just have to ask your questions to that participant, and then your questions will be addressed at the end of the lecture. And also, like, if you have questions related to panel, which would be from 3 to 4, as you can see on the screen, then those panel questions you can also fill one form related to panel discussion that would also be provided in the chat section. So you can just go there and enter all your questions or doubts in that form, and those will be addressed in that panel discussion timings. And there you can also ask your doubts yourself. Like, here we have kept this restriction that your doubts, we will deliver your doubts to the teachers, but there you can yourself ask your doubts. And this was it. You can just enter your questions during the lecture, which you have questions, you can enter those questions or deliver those questions to task moderators, participant name task moderators. So I would request everyone to have their lunch. They can either remain connected to this meeting, or they can also leave this meeting and join the same link at 1:40, 5 minutes prior to start of the lecture.
Okay, thank you, Pramit. You can also have a lunch.
Okay.
Okay, guys, we can maybe pause the live session and start again the live session at 1:40,
Okay, ma'am.
1:45.
Sure.
And you
Okay,
can also
ma'am. I
pause
will
the
do that.
recording. Yeah. Okay. So yeah, see you guys at 1:45.
Hello.
Hello. Good
Hi.
afternoon, sir.
Hey, so shall I share my screen?
So actually, we would like to introduce about ourselves. Like we would like to tell you about us, like what we do.
Yeah, great. That sounds very good. Thank
Okay,
you.
sir.
Tell me.
Okay, so I welcome you all after a short break. So here's a brief introduction about us. So we are Thapar Amateur Astronomers Society. And in this society, basically, we all are like-minded people, and we all love astronomy and we all love physics. So we basically come together and celebrate our love for astronomy and physics. So for that, we organize various events together. And the first event, as we are a part of right now, is Eureka. Eureka, in this event, we organize various competitions and quizzes as well, and lecture symposium as well, of which we are part right now. And then we have Akash Ganga. In Akash Ganga, basically, we invite school students and we organize various workshops for them, like telescope making workshop and other very interesting workshops for them, so that, to embark in them that future scientist. And then we have, last but not the least, group discussions. In these group discussions, we express ourselves, we share our knowledge, and we like discuss about the various topics with among ourselves, and we enjoy a lot in these sessions. So I hope you enjoyed our event. And now I would request Ishan to kindly introduce our next guest lecture.
Hello. Yeah. So we at TAS welcome sir, and I would like to introduce sir to our audience. Dr. Nissim is a professor at National Center of Radio Astrophysics of Tata Institute of Fundamental Research. He is famous for sharing his thoughts and knowledge on studies on the evolution of electron-proton mass ratio. He is also a member of International Astronomical Union. We welcome you, sir, today.
Thank you. It's a pleasure to be here.
Pramit, you may stop sharing your screen, sir.
Okay. Yeah.
Right. So just let me know when I should begin.
Yes, sir. You may begin.
Yes, sir. Yes.
Great. Excellent. So I'll just share my screen and then we can take things from there. Okay. Can you see my screen?
Yes, sir.
Excellent. Okay. So I'm going to be telling you today about radio spectroscopy. And the picture that you see in the background is of the giant meter wave radio telescope, one of my pet telescopes, and which is about 80 kilometers from us here in Pune, at a place called Narayangaon. It's about 30 antennas, and unfortunately, it is really sad to have to tell you that the person who started radio spectroscopy in India, in fact, the person who started radio astronomy in India, Govind Swarup, passed away about 2.5 months ago. But if he were not had not been around and had not led this field for nearly 60 years, we would certainly have not been here at this time. So yeah, so I guess this talk in many ways is a tribute to Govind. So this is a broad outline of the talk. I should mention that I tend to speak really fast, and I always kind of remind myself to speak slowly in talks, and I always forget. So in case anybody feels I'm going too fast, which I'm sure all of you will, just stop me. I think you can unmute yourself and stop me, and I'll try to slow down for at least another 5 minutes.
Okay, sir.
Fine. So this is a broad outline of the talk. I'll try to convince you that you should love radio spectroscopy at the beginning of the talk by contrasting it with other wavebands of the electromagnetic spectrum. It's not necessary to love radio astronomers, but radio spectroscopy is a good thing to love. I'll tell you a little bit about a few good radio lines. And I will give you the caveat that the problem in the radio, as you will see right at the end, is that we have a ton of interesting lines which can probe the physics and the chemistry of the interstellar medium and of galaxies. And so I have chosen lines with a strong cosmological bias, a strong bias towards galaxy studies. And there's a reason for that. It'll kind of be in keeping with the nature of this talk. And the problem that I always have when I give general talks, 1 hour talks on something like spectroscopy, is that there's not enough time to go into detail. And so I tend to wind up, kind of telling you about 7 or 8 things that you can do with spectral lines, with certain spectral lines. And this gets hard, especially for the audience, but also for me. But from the point of view of the audience, you kind of get, this big picture view of about 7 or 8 things. and they all are very different. And so you get this view that, okay, there are lots of stuff that can be done. And I've chosen today to do something completely different, which is to tell you about two pieces of work that we have done using radio spectroscopy. And I will do two things in there. One is that I will emphasize the complementarity between radio and optical, or between radio and other wavelengths. And that is, I think, an important message to take home in astronomy, that you learn much more about the universe when you use multiple tools, and the different tools give you access to much more information than any single tool would. And the second thing I'd like to emphasize is that both of these things are, primarily because of my personal interests, both of these are focused on galaxy evolution, and that's just to kind of keep it coherent. And so that you get at least a semi-consistent picture from these two techniques. And so these are the two things I will be talking about. I'll be talking about the use of the 21 centimeter line of atomic hydrogen, which will be called H1 from now on, to measure the atomic gas mass of high redshift galaxies. And that's some work that Aditya Chaudhary, a student at NCRA, has done over the last couple of years. And the second is to use the ionized carbon C2 158 micron line, which is at a frequency of 1.9 terahertz, and redshift that line down to about 350 gigahertz to actually measure or detect high redshift disk galaxies. So I'll tell you both of these things towards the end of the talk. But why should you care? Why should you love radio spectroscopy? Why shouldn't you just say, hey, look, optical is wonderful. I mean, optical work has been done for the last 400 years, and radio is young. So the first reason why you should love both the optical and the radio is shown in this plot over here, which shows the atmospheric opacity as a function of wavelength. And this stretches on the left of the figure from gamma rays all the way up to the extreme radio, which is at about, say, 10 megahertz. So these are gamma rays on the left and radio on the right. And the wavelengths, if you can kind of squint, you'll see that the wavelengths are shown in the top panel over here, which shows a solid line. And that solid line, or the yellow ochre region over here, shows the atmospheric opacity. And what you see is that the opacity is basically 100% at the gamma ray and ultraviolet wavelengths. And that means that you basically cannot observe through the atmosphere. You cannot have a gamma ray or an ultraviolet telescope on the ground, on the planet Earth. You have to go to space. And that is, for example, why the Hubble Space Telescope is in space. Then you come to a point which is entering the optical, where suddenly the opacity dips and it goes close to zero. Not quite zero, but close to zero. And that's for a very small region in wavelength space. And then it rises again, the opacity. And then in the near infrared, over here, about 1 micron to 2 micron, you can still do observations, but the opacity is rising. In the mid infrared, again, you can do a few observations, but the opacity is rising. That goes all the way up to about 10 or so microns. And this is from very high altitudes, from Mauna Kea at about 4,200 meters above sea level. And then you come to the far infrared, the late, mid, and far infrared, where again the opacity is basically 100%, and you can't see through the atmosphere. Again, you have to go to space. So that's why, for example, satellites like Spitzer and Herschel were sent to space. And then the opacity starts to drop at about 1 millimeter. And then you have this steep decline where the opacity goes to basically zero from around a centimeter or so to all the way up to maybe about 20 meters or so. 20 meters corresponds to about 10 megahertz. And that's the point where the opacity again rises to 100%. What this tells you is that you can observe the sky, you can observe the universe from the ground at essentially two wavebands. One of them is the optical, which we know and love, and that kind of shows you the optical spectrum with blue on the left and red on the right. And then the radio. And the radio, as you can see, is a vast frequency range. It stretches all the way, in terms of actual observations, from about 1 millimeter, if at 0.3 millimeters, all the way out to 10 meters. And the reason this is important is that the fact that you can do observations from the Earth at the radio and the optical means that you can build big telescopes. And your sensitivity in astronomy is directly proportional to the size of your telescope. The bigger the telescope, the better it is. So being able to observe from the ground is really special. And that makes the optical and the radio very, very special. Just to give you a feeling for this, the Hubble Space Telescope is what we think of as a fantastic telescope. The Hubble Space Telescope is just 2.4 meters in size. The biggest telescope today on the planet is the Gran Telescope Canarias, which is 12 meters. There are a number of 8 to 10 meter optical telescopes. And there are no big radio telescopes. The biggest radio telescope in the sky is, I think, 5 meters in size, ever launched. And on the ground, there are 500-meter dishes, 300-meter dishes. The Arecibo dish, which I guess some of you have heard has gotten damaged recently. And the GMRT, which is 45-meter dish. These are huge dishes, and the collecting area is massive. And this means that the sensitivity for observations from the ground in the radio and the optical is much, much higher than you can achieve from space. And that means that you can detect really faint sources. The radio is special because the frequency range is so large. It goes from 10 megahertz up to approximately 1 terahertz, which means lambda wavelengths of about 13 meters to about 0.3 millimeters. And that's a gigantic frequency or wavelength range. For comparison, the optical sky goes from about 3,000 angstroms, 3,300 angstroms, to about 10,000 angstroms, a factor of 3. The radio is much more like 3 or 4 orders of magnitude in wavelength. And that's why the radio is special. The fact that you have this wide frequency coverage means that you have access to much more information about the universe. And what I've done in the figure, in the bottom part of the figure, is that I've indicated 3 important spectral lines, the 3 most important spectral lines in radio. And you'll see one of them is not really in radio. One of them is the 21 centimeter line, which I will talk about in the first part of the second half of the talk. The second is the CO line, the carbon monoxide line, which traces molecular gas. The 21 centimeter line traces atomic gas. And both of these are in clean windows of the sky, which means you can observe them from the ground or from mountain tops. And the third is the ionized carbon 158 micron line, which is actually at 160 microns, 158 microns. And that you can see is sitting in this far infrared obscured region where you can't observe from the ground. But the beauty of cosmology is that high redshift galaxies are very far away, but they're at high redshift. And what that redshift means is that their spectral lines are shifted by a factor of 1 plus z to lower frequencies. This means that the 1.9 terahertz or 158 micron carbon line gets redshifted down for an object at high redshift. And so it moves towards the right in this figure for an object at high redshift. And this means that you can actually observe this line with radio telescopes on the ground for high redshifts. It's hard to observe it in the nearby universe, but you can observe it in high redshift galaxies. And that makes it a lot of fun. So that's the first reason why you should love radio. The next reason is that radio is special because unlike optical, radio is not affected by dust. And optical and UV observations are completely affected by dust attenuation. Basically, galaxies contain dust. They contain silicates, graphites, carbonaceous species, all kinds of stuff. And the dust grains basically block optical and UV light. And a nice example of this is shown of a dark cloud in the Milky Way called Barnard 68. The top figure over here shows a VLT optical image. And you can see this region, and the VLT is a big telescope with 8 meters. And you can see this kind of black region over here. So there's lots of stars over here, it looks beautiful. And then suddenly there's this completely black region. It looks like there's nothing at all over there. And this is the region of the Milky Way, right? So there should be stars everywhere. But you don't see them in the optical. And this is a very deep observation with a very big telescope. And with the VLT, Joao Alves et al. Also did a near-infrared observation. And then they barely start to see these faint stars popping up. And the reason they can't see these stars is that these stars are sitting inside a very dark cloud. The cloud is dark because it has tons of molecules and dust inside it. And the molecules and dust are basically blocking the light of the stars inside them and of stars behind them. And therefore you can't see the stars. And that's why it looks black in the optical. And so of course, there's nothing you can do about this. You simply have to. The problem is that at short wavelengths, high frequencies, observations are affected by dust obscuration. That's all you can do. And the radio, being long wavelengths, is not affected by dust at all. Another beautiful example of this is the source called HTF 850.1, which is the brightest submillimeter source in the Hubble Deep Field. So the Hubble Deep Field is one of the deepest images of the sky taken with the Hubble Space Telescope. And this is the HST image of the Hubble Deep Field. And you can see a bright galaxy over here and another bright galaxy kind of in an arc over here. And you can see a cross in between these two. And that cross marks the location of a very bright source in a submillimeter image of the field. And submillimeter is very good because it actually is picking out dust emission. If you have dust heated by ultraviolet photons from stars, the dust emits in the far infrared, which gets redshifted to the submillimeter. And so what people saw was this really bright source in the submillimeter. And so they said, hey, this source must have a counterpart in the optical. And they went and looked. They went really deep with the Hubble Space Telescope, and they saw nothing at all. And then 20 years later, nearly 20 years later, 15 years later, radio observations were used by Fabian Walter and collaborators. And what they did was that they imaged this this field in the C plus 158 micron line of ionized carbon. And they found this beautiful emission over here, which is shown in contours on top of the Hubble Space Telescope I-band image, where again, you can see this bright galaxy on the left. You can see this other galaxy on the right. And you can see there's nothing at all in the color map at the location of the C plus emission. And that's because all the optical and ultraviolet light of this galaxy is blocked by the dust in the same galaxy. And this galaxy turns out to be at a redshift of 5.2. It's one of the most massive galaxies in the universe at those redshifts, and you don't see it at all in the optical. So you need radio to actually identify these galaxies and then find out what they are. And that's just because of dust. So dust is a big reason why you really like to work at radio wavelengths. You're not affected by dust at all in the radio. Next, one of the important things in astronomy is angular resolution. You want to be able to distinguish, to resolve out sources, to distinguish, to measure the size of sources, to separate between sources in the sky. And for that, you need to have resolution. You need to be able to separate, to break up sources into their constituents, if you like. And the resolution of a telescope is basically lambda by d. The lambda is the wavelength, and d is the telescope diameter. I put diameter in quotes because, for example, when you have an interferometer, which you have in the radio often, then what happens is that what matters is not the physical diameter of a single dish of the interferometer. The interferometer is made up of, for example, many dishes. So, for example, the GMRT, the Giant Meter Wave Radio Telescope that we heard about later, is made up of 30 dishes, each of which is 45 meters in size. So if you think of the sink of each of those dishes, the D is 45 meters. But the dishes are spread out over a distance of 25 kilometers. And what you're doing is that you're synthesizing a telescope of diameter of 25 kilometers. So the effective diameter of an interferometer is 25 kilometers. So for example, for the Hubble Space Telescope, lambda is about 6,000 angstroms in the optical band. The diameter is 2.4 meters. And this tells you that the resolution is about 0.05 arc seconds. And that's pretty fantastic. 50 milliarc seconds is a great resolution in the optical. And that's about the best you can do with any telescope in the optical today. The Very Large Array in New Mexico, which is the sister of the GMRT in the US, which basically works at higher frequencies than the GMRT, it goes up to a frequency of 43 gigahertz or down to a wavelength of 7 millimeters. And it's got a longest baseline. So it's got 27 antennas, which are shown over here. It's got a longest baseline of 35 kilometers, slightly longer than the GMRT. And if you divide lambda by d, you wind up with R of about 40 milliarc seconds. So similar to the VLA, similar to the Hubble Space Telescope, slightly better. When you go to the Atacama Large Millimeter Submillimeter Array, ALMA, which will be the focus of the last part of the talk, that's the ALMA array sitting on the Shashnantor Plateau of the Atacama Desert with an absolutely beautiful volcano, Likan Kabur, in the background. ALMA goes all the way up to 900 gigahertz, which is about 0.3 millimeters. And ALMA's longest baseline is about 16 kilometers. And this means the resolution of about 4 milliarc seconds. So that's a factor of approximately 10 higher than or better than the Hubble Space Telescope. And it gets better. If you look at the Very Long Baseline Array, which is a 10-element interferometer in the US, which is spread over the entire US, going from one antenna in Hawaii, one antenna in Puerto Rico, and 8 antennas over the entire contiguous United States. The longest baseline is about 10,000 kilometers, and lambda, the wavelength, is about 7 millimeters. You can actually go up to 3 millimeters, but I've just chosen 7 because that's a high sensitivity part of the receiver. And that corresponds to a resolution of about 0.15 milliarc seconds. So this is now even better than ALMA. It's a factor of about 20 better than ALMA. And I guess all of you have seen those beautiful images of the black hole, of the gas around the black hole in M87 with the Event Horizon Telescope. That's an example of a similar radio telescope like the Very Long Baseline Array, but that has a resolution mostly because the wavelength is even shorter. That's at 230 gigahertz. This is 43 gigahertz. The Event Horizon Telescope is at 230 gigahertz, and that's a resolution of 25 micro arc seconds. And that's the reason you can actually go down to the level of nearly the event horizon of a massive black hole. So radio gives you spectacular angular resolution, and that's an important take home from this. Next, the final thing is that the most important constituents of galaxies are dark matter, of course, which we can't observe with electromagnetic radiation, and then stars, of course, which we know and love and which we can see in the optical. But there's an extremely important additional component called gas. And the gas is, for example, typically hydrogen. 75% is hydrogen, about 25% is helium. The gas is atomic, a mix of atomic, molecular, and ionized. And if you want to understand galaxies and galaxy evolution, you must understand both the stars and the gas. The gas is called the interstellar medium. And an important take home is that galaxies look really different in the stars and the gas. So this left panel over here, the left two panels, show you a famous galaxy, NGC 6946, with a Hubble Space Telescope image in the optical. And you see these beautiful spiral rings or spiral arms of this galaxy, absolutely gorgeous spiral arms. And in the middle panel shows you a picture of the same galaxy, but this time in the 21 centimeter line. And this picture is an atomic hydrogen. And it's on the same scale. And what you see over here is that the galaxy is much, much, much bigger in atomic hydrogen than in the stars. It's about a factor of 2 bigger in the atomic hydrogen, 2.5 bigger. Some galaxies are up to a factor of 10 bigger than the stars, in the gas than in the stars. Basically, the gas is sitting out in a much larger disk, and the atomic gas flows in, cools, forms molecular hydrogen, and then the molecular hydrogen converts to stars. So now if you're only looking at the stars using optical observations, you will get a very biased picture of the galaxy. There's much, much, much more both size and mass in atomic hydrogen than there is in stars. And the important thing that should be emphasized is that the critical spectral lines of the interstellar medium, which you must understand to understand galaxies, for example, the 21 centimeter line, the carbon monoxide rotational lines, all lie at radio wavelengths. So if you want to understand the ISM, you must work in the radio. The second thing is that with radio interferometry, using these multiple dishes and combining them to synthesize the radio telescope, you can actually do better than simply making an image of the sky. You can make 3D images, which means that you make an image of the sky as a function of frequency. And that is wonderful. This is what is called, these are what are called spectral cubes. And this allows you, because spectral lines give you the advantage that you can actually measure velocity. So a spectral line comes at some frequency. But now suppose the gas emitting that line is moving towards you, the observed frequency will be blue shifted. It will be just by the Doppler effect. On the other hand, if the gas is moving away from you, then the line will be red shifted. And this means that I can measure kinematics of the emitting gas by simply making a 3D spectral cube in a spectral line. And this lets me measure velocity fields and trace kinematics. So what is shown in the right panel over here is an image using the Westerbork synthesis radio telescope, a very deep observation of the galaxy M33, which is a lovely disk galaxy in the nearby universe. It's very close to M31, the Andromeda galaxy. And this galaxy is a nice disk galaxy. And what's happening is that the blue contours so this is the velocity field. The blue contours over here, the blue colors over here are indicating gas that's moving towards us. The red over here is indicating gas is moving away from us. And the yellow is gas which is basically at rest relative to the center of the galaxy. So what's happening is that this is a disk galaxy, like the Milky Way, which is inclined to us in the sky, and it's rotating. So the upper half, the right half of the galaxy is moving away from us, it's spinning away from us, and the left half of the galaxy is spinning towards us. And this is a signature of galaxy rotation. And this is actually beautiful. I mean, you can actually see a galaxy, just by measuring its spectral lines, you can measure its rotation, its kinematics directly. You can check whether, for example, turbulence is important or whether the galaxy is moving uniformly. So you can trace very fundamental physics. And in fact, galaxy rotation has been used by measuring the velocity as a function of the distance from the center of the galaxy, what is called the rotation curve. So you measure the rotation speed as a function of distance. And what people found in the 70s was that the rotation was too fast to be explained by the matter that you could see in the galaxy. And the rotation speed was just, it didn't drop with distance as expected if all the mass was where you see the light. What happened was that the rotation speed seems to stay flat or even rise at large distances. And that led people to realize that there's a lot of dark matter in galaxies. And this has now been shown to be one of the fundamental constituents of the universe, containing about 20% of the mass density of the universe. And that has come predominantly or originally from galaxy rotation curves in the 21 centimeter line mainly. And the reason 21 centimeter is so important over here is that the 21 centimeter line allows you to go very far in galaxies. Because as you can see, NGC 6946 is so much larger than in the gas than in the stars. So you can measure the rotation curve out to 2.5 times the distance in 21 centimeter than you could do in the optical. And this allows you to probe the velocity field at much larger distances from the center of the galaxy. But this picture of a velocity field of this blue thing on one side and red thing on the other side is the classical signature of a disk galaxy. So I'll ask you to bear that in mind for the second half of the talk. So moving on, those are the reasons why you should like radio spectroscopy or why you should like radio astronomy at some level. So what are the kinds of lines that we are thinking about in the radio? So I'm going to again just touch on a few of these lines. And as I said, this is really biased towards cosmology. For example, I'm not going to mention all the wonderful lines that you see in, for example, in complicated molecules between, let's say, 43 gigahertz, 40 gigahertz, and about 1 terahertz, which allow you to do all kinds of stuff. It allows you to probe organic molecules, for example, like glycine, protein molecules, and look for the hints of life in molecular clouds. I'm not going to talk about protoplanetary disks around stars. I'm going to focus completely on simple lines, relatively simple lines. And the first of these is the 21 centimeter line, the hyperfine line of atomic hydrogen, which I said I'm going to call H1, which is at 1420.4 megahertz, or a rest wavelength of 21.11 centimeters. And this line was actually predicted during World War II to exist during World War II by a PhD student, Van der Hulst at Leiden. And this line has turned out to probably become the most important line in astronomy. It's been used for so many things in astronomy that it's kind of not funny. And I'm not going to list them. I'm just going to list two of the things that are really important. The first one is that the line, the 21 centimeter emission line, lets you, the strength is proportional to the atomic gas mass of galaxies. And so this lets you measure the atomic gas mass of galaxies. And the atomic gas mass is a fundamental constituent. The atomic gas is a fundamental constituent of galaxies. So measuring the mass is doing a fundamental measure of the gas properties of galaxies. The second thing is that it lets you measure galaxy rotation curves unbiased by dust. You can basically see through the galaxy and measure its velocity field. And that lets you do, for example, things like inferring the presence of dark matter. And that came to 21 centimeter studies in the 1970s. And I'll talk a little bit more about 21 centimeter in a short while. CO lines, carbon monoxide lines. Carbon monoxide actually is not the most important molecule in the universe. Obviously, the most important molecule is molecular hydrogen. But molecular hydrogen does not have any lines. It's a sad molecule because it's a homogeneous molecule. It's hydrogen and hydrogen. And so it turns out that the rotational lines in such a molecule are forbidden. And therefore, you don't see rotational lines from H2. The vibrational lines are, because the molecule is so light, are in the mid-IR, in the far and mid-IR. But what is worse is that the vibrational lines have extremely high excitation temperatures, which means that you can only see these lines when the gas is very hot, about 500 Kelvin or so. And a molecular hydrogen or molecules in galaxies are at very low temperatures typically, more like 20, 30 Kelvin. And this means that you never see those almost never see those vibrational lines except in very special circumstances. So as a result, you can't see H2 directly. The second most abundant molecule in the universe is CO, carbon monoxide. The thing that we hate, on the planet is what we love in astronomy. And the CO molecule has what are called rotational lines in this molecule at a frequency of about 115.27 multiplied by J, where J is the rotational quantum number in gigahertz. So it's got this ladder of lines at 115 gigahertz, 230 gigahertz, 345 gigahertz, 460 gigahertz, and so on. And these basically happen because the rotational kinetic energy of the CO molecule is quantized. So you can keep increasing. So as the thing, if you want a physical picture, if the thing spins faster and faster, it has a higher and higher rotational kinetic energy, and the kinetic energy levels are quantized. So which means only some levels are allowed. And the lowest, the ground state in rotation is at 115.27. The first excited state is at 115.27 gigahertz above the ground state in frequency. Now, the reason the CO lines are so important is that, as I said, you can't use H2. You can't observe H2 directly. CO allows you to measure the molecular gas mass of galaxies using relations between CO and H2. And it is today the best tracer of the molecular gas. So if you want to understand stars, you need to understand the gas. 21 centimeter lets you probe the atomic gas. CO lets you probe the molecular gas. And both of these together give you a picture of the bulk of the interstellar medium. The third line, and the line that I'm going to focus on at the end of the talk, is, as I said, the ionized carbon 158 micron line. And that's at 158 microns in the far infrared. So it's not really a radio line. It's in the far infrared. But as I mentioned, this line is redshifted into the radio band for high redshifts. Redshifts larger than about 1. You can observe this line from the ground. And this is a fine structure transition. It's an ionized carbon at about 1.9 terahertz, 1901 gigahertz. And this line is kind of special because it's the strongest cooling line. Carbon is a very abundant species. And this line lets gas basically cool. So you can imagine, molecules being, or atoms being at some temperature, and those atoms being excited to some temperature, moving to some excited state, and then radiating out their energy. And the maximum radiation goes in this carbon line at 158 microns. And this line is so strong, it contains, in that one narrow, tiny line, it contains typically about 0.5% of the entire luminosity of a galaxy. So the Milky Way, for example, radiates about 0.5% of its luminosity, about 1/20th of its entire luminosity, all the different gamma rays up to radio, is radiated in this single, very narrow line at 158 microns. So it's a really special line. And this line is really strong, and the strength matters because the strength means that this makes it wonderful to map the kinematics of high redshift galaxies. So the kind of stuff that you do with 21 centimeter in the nearby universe, you can hope to do with the ionized carbon line at very high redshifts. There are strange lines called H2O, water, megamasers. And these lines are observed when you have gas in an accretion disk around active galactic nuclei, around massive, supermassive black holes. And this is really black belt radio astronomy. But this, it turns out, allows you to measure black hole masses because these lines come from an accretion disk. And the accretion disks are typically in Keplerian motion. They're just spinning around the supermassive black hole. And so using radio astronomy, you can actually, using very long baseline interferometry, you can actually observe the different parts, different emitting regions, and measure how they are rotating. And then use the Keplerian expression p squared proportional to r cube. You measure the period, you can actually get explicitly the distance, the actual distance. And because you know the angular distance, the angular separation from the black hole to these emitting regions, you can now get the actual distance to these chaps. So you can actually measure both black hole masses, and you get masses of about 10 to the 7 or so solar masses for the black holes. And most excitingly, you can measure the Hubble constant. So it turns out that the entire cosmological distance scale today, based on the Hubble constant, is based on observations of a single H2O megamaser, the famous megamaser NGC 4258, from Mark Reed and collaborators with the very long baseline array. And that's a superbly exciting thing, which we can chat about for hours if you like. And last, I thought I should briefly mention another really strange group of lines from ammonia, NH3, methanol, and OH. And these are all really complicated, complex molecules. But the beauty of these molecules is that they have all kinds of lines. they have lines from very different physical mechanisms. They have, for example, ammonia has inversion lines, where the hydrogen atoms in the ammonia molecule basically have a mirror reflection symmetry. They can push on the other side. It's a quantum tunneling effect. And it turns out that you will see lines because of this tunneling. And you can compare those lines with rotational lines in ammonia, which it also has. And you can use this comparison to probe changes in the fundamental constants of physics, like the fine structure constant, the proton-electron mass ratio, and so on with redshift. And that's, of course, the area of much interest today. Methanol is absolutely wonderful for this as well, because it's so complicated, it has a lot of lines, and you can actually study the physics in great detail in the lab, in theory, and at high redshift. So this is another area of much interest. Okay, so this kind of gives you a big picture view of a small number of lines, but I'm going to jump now to talk about two particular projects. The first, using 21 centimeter emission to measure the atomic gas mass of high redshift galaxies. So as I said, galaxies are made up of stars and gas, and about 75% of the gas is hydrogen by mass. And a galaxy, if you want to think of a galaxy is basically a black box. It's not really a black box, but it's like a black box in which you have atomic gas getting converted to molecular gas. It cools and converts to molecular gas. The molecular gas undergoes, collapses under its own gravity and forms stars. The stars then live their lives, and then they go boom, they go supernovae. The supernovae, in the explosion, they produce metals, and they return the metals to the gas. And the metals that are returned to the gas cause further cooling of the atomic gas, which causes further formation of molecular gas, which causes more stars and more supernovae. In addition, the metals are thrown out into the circumgalactic medium, into the gas around, into the region around the galaxy. And then they fall back and they drag gas from the circumgalactic medium onto the galaxy, causing further formation of atomic gas, and then further molecular gas and further stars and so on. So that's the life cycle of a galaxy. But what all this tells you is that atomic hydrogen gas, H1, is the primary fuel for star formation. And I've shown you this pretty picture of NGC 6946 from Renze Boomsma's PhD thesis before. And you can see that there's a ton of atomic gas in galaxies. It stretches out much beyond the optical. And that's kind of consistent with this picture. Gas flows from outside galaxies into the outskirts of galaxies. And then the gas moves towards the center, cools and forms molecular hydrogen, which then fragments into molecular clouds and then forms stars. And the way you observe the H1, the atomic hydrogen, is via the 21 centimeter line. And I said that the 21 centimeter emission strength is proportional to atomic hydrogen gas mass. And this is the only way of measuring the atomic hydrogen mass of galaxies. So what is this 21 centimeter line? The 21 centimeter line is basically a line in the ground state of atomic hydrogen. So most of you will be familiar with the usual electronic transitions, the Bohr atom, in which you have the principal quantum number, n equal to 1, n equal to 2, n equal to 3, and so on. And then you have the Lyman series, the Balmer series, the Paschen series, where you have the electron doing jumps from different principal quantum number levels to the next lower level or lower levels. The 21 centimeter line, and you can kind of picture the Bohr series or these electronic transitions in a kind of a semi-classical way, where, in fact, the Bohr atom is fairly semi-classical, where you just say that for some reason, for some unclear reason, angular momentum is quantized, and you're allowed to only have these levels, and then you jump down. The 21 centimeter transition is the first of the genuinely, purely quantum mechanical transitions. It happens because of spin. And spin is a completely quantum mechanical concept. It's got no classical parallels. And so what happens in the 21 centimeter line is that in the ground state of atomic hydrogen, you have the proton and the electron, right? And that's all you have in a hydrogen atom. And you have these two spins, one of which is upwards, one of which is downwards. And so there are two possible states. One state has the spins of the proton and electron parallel, and the other state has the spins anti-parallel. And it turns out these states have slightly different energy. The anti-parallel state is at a slightly lower energy. And so this means that you can make a spin flip transition in which the electron spin jumps from being parallel to the proton spin to being anti-parallel with the emission of a photon. And that photon comes out at 21 centimeter, 21.11, 1420.40575 megahertz. And that's the 21 centimeter line. So it's a spin flip transition. And as I said, it's wonderful for probing atomic gas. It's this truly beautiful line, but it's also a pain. It's a pain because it's hyperfine. It's coming with a hyperfine structure, and the line is very, very, very weak. To give you a handle on this, the Einstein A coefficient for spontaneous emission in 21 centimeter is 10 to the minus 15 per second. And this is ludicrously small, right? And this is the probability of spontaneous emission in 21 centimeter. For comparison, one of your favorite Lyman alpha or Balmer alpha or whatever lines from jumping from principal quantum number levels has an Einstein A coefficient of about 10 to the 8. So those lines are about 23 orders of magnitude stronger than the 21 centimeter line. So you might say this line is a pain. Why do I want to waste my life observing it? Of course, the reason you want to waste your life observing it is that the line is so powerful in probing gas in galaxies. And the reason you can detect it is that there's lots of atomic hydrogen in galaxies. So there's lots of gas, so although the line is weak, you still have a chance of seeing it. And the line is super interesting. But sadly, because the line is so weak, it's very hard to detect at cosmological distances. So one way of thinking about it is that if you look at this beautiful image of NGC 6946, this galaxy is about 7 megaparsecs from us. So about 22 million light years from us. If I took this galaxy and placed it at a redshift of 1, this line or this emission would be 1,000,000 times fainter, because a redshift of 1 corresponds to about 7,000 megaparsecs in terms of luminosity distance, and the signal falls like 1 upon distance squared. So this line would be a factor of 1,000,000 weaker, which means that it turns out you will require to detect it like this, you'll require 1,000,000 squared amount of time to detect it, which means that if this observation took 10 hours, then you will require 10 to the 12 multiplied by 10 hours to detect a galaxy like this with the same telescope at a redshift of 1. And that kind of indicates that, this is going to be really hard. Nobody has 10 to the 12 hours to observe it. And so that is the problem. How do you actually use the 21 centimeter line, or how do you measure the atomic hydrogen mass of galaxies at high redshifts? And the reason this is really important is that over the last 20 years, we've learned a lot about stars in galaxies. And this plot shows you a picture of the star formation activity in galaxies as a function of redshift. Starting from redshifts of 8, what you can see is that the star formation activity in galaxies rises from redshifts of 8 to redshifts of 3. And then it's about flat. There's a plateau at redshifts of 1 to 3. And then there's this remarkable decline from redshifts of 1 to today. So what's happening with redshifts of 8 to 3 is that gas is building up in galaxies and you're forming more and more stars. And then there is this epoch where star formation activity seems to kind of plateau. And that's called the epoch of galaxy assembly. Basically, half of today's stars were formed at this redshift range, redshifts of 1 to 3. So that is a really interesting epoch in the universe. And then after that, there's a spectacular decline. And the y-axis is on a log scale. So the amplitude of the star formation activity is 10 times higher at a redshift of about 1 than it is today. So it is about star formation galaxies was about 10 times higher about 8 billion years ago compared to today. So this really begs the question, why did the star formation activity slow down? And the only way of answering this really is to measure the hydrogen mass in these galaxies, which is the fuel for star formation. There has to be something happening to the fuel. And so you need to measure the hydrogen mass. But I've just told you that I can't measure the damn hydrogen mass because the 21 centimeter line is weak. So what do I do? And the solution, of course, is that you can try something. And as I said, so one approach is that you can basically spend more and more observing time with bigger and bigger telescopes. And maybe you can build even bigger telescopes. So people are trying this right now, but it's very hard at redshifts larger than about 0.3 or so. It's really hard to detect 21 centimeter emission. The highest redshift detection today of a single galaxy is at 0.376 from Jimena Fernandez et al. With the VLA. We have a bunch of detections at about redshift of 0.2 to 0.3. But beyond that, there's nothing. And so what Jairam Chengalur and Martin Zwan came up with about 20 years ago is that you can use a cute technique called stacking, where you can combine the signals of 21 centimeter emission from multiple galaxies with known redshifts. And this allows you to measure the average atomic gas mass of those galaxies. So what is stacking all about? So stacking is basically a thing where if I have a large number of galaxies, which are shown over here, in my spectral cube, and I know their positions and redshifts, So this shows you small cutouts now for each of those galaxies. I can simply add those cutouts together. I can align these galaxies in velocity and in space. I can just put them on top of each other and simply add the 21 centimeter signals from all these galaxies. When I add the signals, the noise, and I take the average, the noise will go down, but the signal will keep adding up. And so what you see over here is at the bottom is the effect of adding more and more galaxies. So numbers increasing starting from 1. It's gone up to 80 now. And I'm just keeping on adding more and more and more galaxies. And what you see in the center of the image is that as I add more and more galaxies and the noise goes down, you start to see the central region, shows emission. It shows a thing which gets redder and redder as I get more and more galaxies. And what you see over here is that you start to see a signal popping up in the middle of this spectral line, in the middle of the spectrum. So basically all of this to the left and the right of this thing is noise. And you start to see this spectral line showing up. And that spectral line is obtained by cut through this cube, through the spectral cube, the stacked spectral cube. And so now with about 300 galaxies added, you can see this line coming out loud and clear over here. And this will go on up to about 400 galaxies. And this demonstrates the process of stacking. So all you're doing is that you're just taking a large number of galaxies. You're using the fact that with the 21 centimeter observations, you probe a number of different redshifts and a large number of galaxies, and then you add up all these signals. And then you get this beautiful detection of emission that you see over here, this nice, beautiful red central circle, and you see this nice line that you see in the nearby universe. And what you've effectively done is that you have combined the 400 galaxies to effectively reduce my observing time by a factor of 20. That's the game. So of course, what you need to do this kind of a thing is a very high sensitivity radio interferometer, which has a wide field of view. The bigger the field of view, the more galaxies there are in that field of view. The second thing I need is a large galaxy sample within the field of view. And the third thing I need is accurate positions and redshifts for the galaxies. And it turns out, of course, we have this wonderful high sensitivity radio interferometer, which is the GMRT, the Giant Meter Wave Radio Telescope, which is the most sensitive interferometer in the world today at frequencies below 1 gigahertz. And it turned out that we had Keck telescope observations. Keck is an optical telescope in Mauna Kea and Hawaii, 10 meters in size. And we had a wonderful survey called the Deep 2 Galaxy Survey, which gave us a bunch of accurate positions and redshifts for a large number of galaxies. So what Aditya Chaudhary did was that he basically covered 11,000 star-forming galaxies in 5 sky regions of the Deep 2 survey. And he stacked 7,500 clean galaxies. And that allowed him to just about barely detect the signal. And that's a signal that he saw from galaxies at a redshift of 1. So this is the first measurement of the hydrogen mass from this epoch of galaxy assembly at a redshift of 1. That's the spectrum that we see cutting through this cube. And what Aditya found was that the hydrogen mass that he got, the average hydrogen mass, can fuel the star formation activity in these galaxies for only about 1 to 2 billion years, which is really short. In the Milky Way, the atomic hydrogen mass is very large, and it can fuel star formation, and the star formation activity is very low. So the atomic hydrogen mass can fuel star formation in the Milky Way for about 10 billion years, 9 to 10 billion years. But in these high redshift galaxies, the star formation rate is so high that the atomic hydrogen will get eaten up within about 1 billion years. And this basically explains that decline in star formation activity that you saw, because it turns out that the time scale that in this figure over here, 1 billion years is shown on the upper plot. You can see 1 billion years is going from about here to here. So by the time you've gone from here to here, you've basically eaten up all the gas in these galaxies. Our measurement is right over here, and there basically is not enough time for more gas to fall into these galaxies and replenish the atomic gas content of these galaxies. So what we think is happening is that the atomic hydrogen is basically not enough to fuel star formation at its very high level at the end of the epoch of galaxy assembly. And that's the reason the star formation activity declines after a redshift of 1. That's the picture that we have today of galaxy evolution. So moving on, I'm going to shift gears and move to even higher redshift. Now, in our picture of galaxy formation and evolution, the basic question we want to understand is how did the universe form these galaxies? We know that the universe was nearly perfectly homogeneous to about 1 part in 10 to the 4, about 400,000 years after the Big Bang. And we know that because of images like this on the top left, which come from the Planck satellite or the Wilkinson map satellite, which show the cosmic microwave background is essentially smooth to about 1 part in 10 to the 4. And the universe is highly inhomogeneous today. It's got all these beautiful galaxies around the place. That's a Hubble deep field made the Hubble Space Telescope. There are billions of massive galaxies, each full of stars and gas. So the question in galaxy formation and evolution is how did we go from the top left picture to the bottom right picture? How did we form these huge, gigantic galaxies from a universe which is nearly perfectly homogeneous and isotropic? And the way this happened is via what is called gravitational clustering, where regions that were slightly more overdense than neighboring regions had slightly higher gravitational attraction, and therefore matter flowed from the underdense regions towards the overdense regions, as you can see over here. So what's happening here is that the blue regions are underdense, the red regions are overdense. And this is a movie starting of a simulation, a dark matter simulation, starting from a redshift of 20 and going down to 0, where you can basically see the formation of a gigantic cluster of galaxies, supercluster of galaxies in the central region. This is about 8 megaparsecs in size. And so there's a huge cluster of galaxies. And this is the picture of the universe. There are these filamentary structures which are flowing into big galaxies. Let's look at this movie again. Starting at a redshift of 20, the universe is nearly uniform. And then you start to see these holes developing, underdense regions becoming more and more underdense, and overdense regions becoming more and more overdense as matter flows along these filaments into the overdense regions. Focus on the central big chap over here. And that's kind of forming a huge supermassive elliptical galaxy in the center of this supermassive cluster. And similarly, there are galaxies forming at the nodes of all of these filaments and other parts of this image. And that's how we think galaxies formed. And so we think this is a reasonably good picture of galaxy formation. But of course, this is dark matter. And what we want to understand is actually the baryons. If you want to understand galaxy evolution, galaxies are really about baryons. Dark matter is just the background. So a huge question is, when do these galaxies of the Milky Way form in the universe? And this is an open question today. And very deep observations with the Hubble Space Telescope have shown that galaxies at redshifts of 3 appear quite clumpy. They don't seem disk-like. They seem like train wrecks, like a mess. Like there's stuff all over the place. The substructure. They don't seem like smooth disks that you see today. There's certainly no spiral arms. And you kind of see disk galaxies by redshifts of 2, 2.5, reasonable disk galaxies. So it looks as though disk galaxies don't form in the very early universe. They take time to form. And this kind of makes sense in the picture of galaxy formation, because galaxies form by merging. And it takes time for disks to settle down into a disk and to have simple rotation dominate over all these merger events and accretion events. It takes time to form a uniform disk. And so this seems kind of okay. Redshifts of 2, 2.5, yeah, you can form disks by then. No big problems. So the question is that the earliest epoch at which these galaxies form? And the problem is that most high redshift galaxies have been identified because they are bright. They're bright usually in the optical, sometimes in the sub-millimeter, but they're bright basically. They're highly luminous galaxies. And this is kind of funny because when you have a merging event, if you have two things merging together, that tends to produce lots of star formation, and that makes the galaxy bright. So identifying galaxies by their brightness in your images could bias against identifying quiescent disk galaxies. A disk galaxy, in order to become a disk, it should almost by definition not be that bright. If it were bright, that would normally happen because there's merging stuff going on. So maybe that's the problem. Maybe that we have, the way we have chosen these galaxies, chosen to go and chase after them, is biasing us towards these merging systems. So what we did was that we chose to target galaxies not because they're bright, but because of their ultraviolet absorption against quasars. So what we did was optical spectroscopy to observe redshifted Lyman alpha absorption against quasars. And then we said, okay, the very strong Lyman alpha absorption means there must be a galaxy at this redshift. And so this is an absorption selection, where the selection is simply by the fact that there is the quasar is a torch in the background, and there's a galaxy between us and the quasar, identified by its absorption signature. And so we said, great. And so this shows you an example of the strong absorption line that we see from this galaxy at a redshift of 4.26 roughly. This is an ionized silicon. It's one of the metal lines from this galaxy. And then we use the Atacama large millimeter submillimeter array to search for the ionized carbon 158 micron line from this object at a redshift of 4.26. And what we saw was this, and this is about 3 years ago. This is a spectral line, the ionized carbon line, from this redshift 4.26 galaxy. And this is the profile. And you can see it's got these two interesting bumps in the profile. It goes high, then it comes down. There's a plateau, it goes up again and comes down again. And this is called a double horned profile. And a double horned profile very naturally arises from a rotating disk galaxy, because what happens is that the part coming towards you, the gas tends to all, if you like, clump together in velocity space. And so the part coming towards you tends to clump together at these negative velocities. The part going away from you tends to clump together in the positive velocities. And so you wind up with two peaks in the velocity profile, one at negative from the blue shifted gas, one at positive, the red shifted gas. And so you get the double horn profile. And that's what you see in the local universe. Double horn profiles are classic for identifying disk galaxies. So what we did is that we used ALMA to actually use, ALMA can be configured into short baselines and long baselines. So the original observations use short baselines. So we used ALMA recently to map the emission at much higher angular resolution. And then we also used the Hubble Space Telescope to image the stars at very similar angular resolution. And what we saw was this. So that's the HST image in the color in the background, in the blue stuff that you see over here. And you can see the HST image looks quite clumpy. It's broken up, the galaxy is broken up into 3 or 4 pieces over here. And the red contours show the ALMA ionized carbon emission. And you can see it's kind of smooth, relatively smooth. But this is a smoking gun signature of a disk galaxy. This is the velocity field with ALMA at a resolution of about 1 kiloparsec. That's the size of the ALMA, that's the resolution of ALMA for these observations. And you can see exactly the same pattern that you saw for M33. You see that this side of the galaxy is red in velocity. This side is blue. What's happening is that this side of the galaxy is moving away from us. This side is moving towards us. And the center of the galaxy is at a systemic velocity, is at the redshift. And this is the classic signature of a rotating disk galaxy. And what this tells you is that massive and very cold disk galaxies, we also used a very large array to measure the molecular gas mass of this galaxy. And we found a huge molecular gas mass, about 10 to the 11 solar masses. So massive cold disk galaxies do exist at very high redshifts larger than 4. And we're now trying to push to even higher redshift to test whether such galaxies exist there. And this turns out to be a key challenge to models of galaxy formation today, which find it very hard to produce such big disk galaxies at high redshifts. So I'm going to now come to the end of the talk. I hope I've convinced you that radio astronomy is a highly lovable field. It lets you do sensitive, really high sensitivity ground-based observations because you can use big telescopes. You can do high angular resolution, and you're not affected by dust extinction. And you observe these critical spectral lines of the interstellar medium, such as the 21 centimeter line, the molecular carbon monoxide line, and so on. I'm not sure why I've gotten muted. It gives you a spectacular window on the interstellar medium. I told you about 2 specific pieces of work, GMRT 21 centimeter stacking to measure the H1 mass of galaxies in the epoch galaxy assembly, where we found that the gas can fuel star formation for only about 1 to 2 gigayears. That explains the decline of star formation activity below redshifts of 1. And I've shown you ALMA C plus 158 micron imaging to identify the first disk galaxy redshifts larger than 4. So these are examples of the science that you can do with radio spectroscopy, addressing cutting edge problems today. And these are the kind of things we hope to do over the next decade or so. And there's lots of other stuff you can do with radio spectroscopy. You can measure galaxy sizes, dynamical masses, gas densities and temperatures, strengths of magnetic fields. You get velocity information, which is critical for measuring the distance scale, velocity fields of galaxies, black hole masses. You can probe the origins of life via searches the complex organic molecules. It lets you find and study the first galaxies, lets you test cosmological predictions, and study planet formation, for example, via gas and protoplanetary disks. It allows you to test the standard model of particle physics and gravity on cosmological timescales via studies of fundamental constant evolution. And I think most of all, it allows you to have a lot of fun. So with that, I'll stop this talk. Thank you.
Thank you, sir, for this lecture. Now, many people have questions regarding radio spectroscopy. So, if I may ask questions from on their behalf.
Please do.
So, sir, Spandan Malik wants to know that if a celestial body moves away from us and at the same time increases its emitting frequency in such a way that there is no apparent redshift, how will radio spectroscopy solve such hypothetical anomaly?
It's not an anomaly. So what you're saying is that, so remember, this is a spectral line, right, that you're observing. The question that you have to ask yourself is, how can the line frequency change with the, as it moves away? The line is coming from some physical mechanism. We observe that mechanism in the lab, right? So if the object is moving away, it's not, unless the physics in the universe changes, the physics is different at the location of that body and today. For example, if you take the 21 centimeter line, right, it's got a frequency of 1420.40575 megahertz. And that comes because of the different energy levels in atomic gas. Now that line has the same frequency, modulo fundamental constant evolution. That line has the same frequency in a different galaxy. Now, if I observe that galaxy, I know that line has the same frequency, definitely, excluding fundamental constant evolution, I know the line has the same frequency, which means there is no possibility of the object moving away and the line shifting to a different frequency. So that's not an issue at all.
Next question is from Bandhan Goyal. At what is the relative velocity magnitude of the ends of M33 3D image? What frequency was used here?
Okay, that's a good question. So the relative velocity is about 350 kilometers per second, approximately. And that's a typical velocity. So that's true of the Milky Way as well. The Milky Way is about 400 kilometers per second. The rotation speed of the Milky Way is about 250 kilometers per second. So if you were looking at the Milky Way from another galaxy, you'd see a velocity spread of about 450, 500 kilometers per second, depending on the exact inclination at which you observe the Milky Way, at which you observe a galaxy. For example, an edge-on galaxy will show you more rotation, a larger velocity spread than a galaxy at, say, 45-degree angle. So the way you observe it is by looking at the 21 centimeter line at close to 1420.4 megahertz, 1420.405 megahertz. And those observations were done with the Westerbox synthesis telescope and the Very Large Array. You can do similar observations with the GMRT.
Thank you, sir. And next question is from Rupinder Pal Singh. Does our galaxy also like similar like NGC 6945 when viewed from other perspective?
Yes, that's exactly what I just said right now. The Milky Way is a big disk galaxy. It's very much like NGC 6946 because these beautiful spiral arms, and the gas goes out much, much, much further than the stars. So okay. in fact, the way in which we discovered many of the spiral arms in the Milky Way was via the 21 centimeter lines. So the measurement of the rotation speed of the Milky Way, Jan Oort in the mid-40s, the reason that the 21 centimeter line was discovered actually was that in the early days of radio astronomy, during World War II, Jan Oort was very interested in the rotation of the Milky Way and who had been using optical lines to study it and realized that dust is a big problem with the optical. So he asked a PhD student, Hendrik van der Hulst, if he could calculate the possibility of radio lines. And van der Hulst identified the 21 centimeter line as a possible candidate that could be detected. And then 7 years later, after World War II, in 1951, two separate groups, Oort and Muller, and Eben and Purcell managed to detect the 21 centimeter line. And since then, Oort and his group basically used that line to map the galaxy. And that's been done in detail for the last 70 years. So yeah, the Milky Way is a beautiful disk, and it's very, very, very like M33. It's much bigger than M33, but it's similar to it.
Okay. So next question would be like, we are engineering students, like we are doing BTech. So like, how can we do research in TIFR if anyone wants to do
we have a lot of engineering students. So the way you do it is that you basically so TIFR. I mean, let's talk about NCRA, because we are a branch of TIFR. We are the TIFR Pune campus.
Okay.
We take students via three approaches. One is the TIFR entrance exam, which is called the GS exam, which happens typically in about December every year. This year it's going to be later because of the pandemic, probably about February or so of next year. We also take students via the JEST entrance exam, the joint entrance screening test, which is normally in February every year, which may be later this year or next year. And then third, NCRA takes students via what is called the Visiting Students Research Program, the VSRP, where every year in the summer, we select students to do projects in NCRA, research projects for 2 months, which usually last from about May to July. And then, and these are students who are entering the final year of their MSc or their BTech or BE. And so between the third and fourth year of your BE or BTech, or between the first and second year of your MSc, or the fourth and fifth year of your integrated MSc. And so all the students are eligible for the VSRP. And then at the end of your project, you'll have a seminar on your project, which will be graded, and you'll have a set of interviews. And then based on that, students will be made offers to join NCRA, the PhD program, from the next year, after they finish their BE or BTech or MSc. So one approach is to summarize, one approach is to take the TIFR GS exam or the JEST exam. I would recommend, of course, doing both TIFR GS and JEST. And then you'll be interviewed. And then you have to just choose NCRA, select NCRA as the place that you want to join. And the third approach is to come via the VSRP.
Okay. Thank you, sir.
Pleasure.
And
Thank you, sir. And the next question is from Bandan Goyal. That can you please briefly tell what were the major hardware changes in the upgraded GMRT?
That's a very good question. So the old GMRT, which is released in 2002, had very narrow band receivers. so the GMRT operates between frequencies of about 150 megahertz and 1420 megahertz, a factor of 10 in frequency. The old GMRT had very narrow band receivers, which covered about roughly 60 to 70 megahertz, 40 megahertz at 230 megahertz, about 20 megahertz at 150 megahertz, about 70 megahertz at 325 megahertz, 70 megahertz at 610 megahertz, and about 500 megahertz at 1.5 gigahertz. And the second thing, which is really important, is that the way in which the interferometer works is that you need to have a correlator. So a correlator is a device which takes the signals from these 30 antennas and cross-correlates them. What you're actually measuring is cross-correlations of the voltages of the individual antennas. And then you carry out a Fourier transform of these cross-correlations to make an image of the sky. So your correlator is the heart of the telescope. And that's a piece of electronics which does these cross-correlations and Fourier transforms. So what you do, so the old GMRT correlator covered a really narrow bandwidth, just 33 megahertz. So the maximum bandwidth was 33 megahertz at a time. And so with the upgrade, the two biggest things that happened were, one, that we built new receivers. So now our receivers give you almost uniform frequency coverage from 125 megahertz all the way up to 1.4 gigahertz. So we go from 125 to 240, then 250 to 500, 550 to 850, and then 1000 to 1500. The gaps are because of very strong interference coming from TV stations at 530 megahertz, and, for example, cell phone bands at 860 and about 940 megahertz. And so we have nearly uniform coverage, which means that we can observe spectral lines at a range of redshifts. But the second thing is that we have this new correlator, and that correlator can cover a 400 megahertz bandwidth at one shot. So we can cover a very wide frequency range at one shot, and that more by a factor of about 13 compared to our old correlator, which is 33 megahertz. And this means that we can observe far more galaxies at different redshifts at one time, and our sensitivity is much higher for continuum studies. So those are two big things for astronomers in the upgrade. In addition to that, there are a bunch of other engineering things. For example, our optical fiber system had to be changed. Our servo system had to be changed to point more accurately on the sky. And then we repaired various things. But the big things for astronomers were the receivers and the correlator. And those actually allowed, the results that I showed you from Aditya Chaudhary. I had done a similar thing in 2016 where I used the old GMRT correlator and the old receivers, and I could do only 33 megahertz. So I did about 850 galaxies in those observations with about 70 hours of data. Aditya, with almost the same time, about 100 hours of time, could do about 11,000 galaxies. So that shows you the power of the new GMRT. Because the 400 megahertz, you're covering a much larger redshift range, because of which I cover a much larger number of galaxies. So we basically increased the number of galaxies by a factor of more than 10, and that allowed us to detect the 21 centimeter emission at a redshift of 1.
Okay, sir. Now, Spandan wants to ask that how does radio spectroscopy overcome the challenges posed by electrical influence over and around celestial bodies and any kind of interference with the transmission or absorption?
So I'm not sure. What do you mean by electrical effects around celestial bodies? That's a strange thing. Can you explain that? I mean, we are looking for electromagnetic signals. So a celestial body like galaxy.
Hello.
Yeah.
Yeah, hello, sir. Actually, I wanted to mean like around Jupiter or Saturn, there's like a influence or a cloud of electrons that does interfere with our with the radio signals and everything.
How does it
So
interfere?
if this, sir, that is what I have read. So that's the thing. I don't know about the
In
details. But
reality, so there are many ways in which this question could be answered. So one thing that happens is that if you have a bunch of electrons, a plasma, right? So you don't have to worry about electrons around Jupiter. But Jupiter is a tiny object. I can simply observe away from Jupiter. I don't have to worry about Jupiter. Jupiter moves in the sky. I simply observe my sources, and Jupiter is not near them. But if I look at the issue, really is more that the electrons around Jupiter are an example of a plasma. And even if you look at any galaxy, there's lots of plasma of ionized hydrogen in the galaxy. Ionized hydrogen is a part of galaxies, and the mass in ionized hydrogen is similar to the mass of a normal neutral atomic hydrogen. And so when radio signals pass through a plasma, they suffer what is called dispersion, which means that radiation at a higher frequency comes slightly earlier than radiation at a lower frequency. And this is most apparent when you observe when you observe pulse signals, for example, from pulsars. If you observe pulsars, which are these rotating neutron stars, you see these very periodic signals in time when you observe them at a single frequency. But now when I observe over a large bandwidth, like say the GMRT 400 megahertz bandwidth, what happens is that the signals should be coming at exactly the same time at the different frequencies. But because of the plasma between us and the pulsar, the lower frequency signals are delayed because the speed of light is dependent in the plasma is not the same at the different frequencies. And so the lower frequency signals are delayed and they come a little bit later. And you have to correct for this. The way and you know exactly how to correct for this, because it turns out this is a new square effect. And so you can actually do something called de-dispersion, either incoherent de-dispersion offline, or what is called coherent de-dispersion, gives you a more accurate dispersion to correct for this. So that's an example of something that you have to do to worry about the presence of electrons in or a plasma between us and the radio signal. And this, of course, is really an issue at low frequencies. It's not much of an issue at high frequencies. But it's a very important issue, for example, for pulsed observations, such as things like pulsars or these very exciting fast radio bursts that people have been observing for the last 10 years or so, and especially most recently, which are these bursts of emission from nearby galaxies. So you see the effects of these plasmas on these very clearly on these very narrow signals in time. And because the effect is to delay the signal at different frequencies. So does that make sense? Or have I completely lost you?
Yes, sir. Yes, sir. Actually, I was unable to unmute myself. So.
Oh, that's fine.
Yeah.
Yeah. And the second part of the question was, how do we handle terrestrial transmissions? And that is a huge issue. That's called radio frequency interference, which is the radio astronomers' three-letter word, if you like. And that's something that we just have to live with. we really struggle to do this. GMRT was put at the way people handle this is that you try to build your telescopes as far away from people as possible. And so when GMRT was planned in the mid 80s, the area around Narayangao was a very quiet farming area, and there wasn't that, it wasn't hugely active. And unfortunately or fortunately, it turned out that there was this boom in farming because the canals in that area. And so the area got really rich, and lots of industries also came up. And industries and humans basically mean lots of interference. And so we have to live with that, unfortunately. But it's still much better in India still today, as compared to, say, the US, where the VLA is. We have much, much, much better interference conditions in India than, for example, even in New Mexico, which is like a desert region in the US. But the next step is probably, that's what people are doing, is to build antennas or radio telescopes far in the desert. So for example, the ASCAP telescope, the Australian Escape Pathfinder in Western Australia, is in a really empty desert in Western Australia, about 1,000 kilometers north of Perth. And then the square kilometer array precursor Meerkat in South Africa is being built on, again, this desert, this high altitude desert in southern South Africa. So these are approaches. You basically go to places which are relatively free of humans. Humans produce interference, and so you need to avoid humans to do good radio astronomy.
Okay, thank you, sir. And now one last question from Yash Singh, that how exactly do we determine the effective diameter of the very long baseline array if the different collectors are non-uniformly located with respect to each other and also quite far away from each other?
How do you determine what?
How exactly do we determine the effective diameter of the very long baseline array?
Yeah, so the effective diameter is just the distance between the between the largest separated antennas. So for any interferometer, the effective diameter is simply I can answer the question in two ways. Formally, a resolution in the sky, you should think of a resolution as a two-dimensional thing, because you'll have a resolution in this direction and in this direction. So you really have, I beg your pardon, Mike, but throat is going down. You have a resolution in the X direction and in the Y direction. So the way you do it is that you take the longest baseline in the X direction, and that will give you a resolution in the X direction in the sky. And you take the longest baseline in the Y direction, and that will give you the longest the resolution in the Y direction in the sky. And that gives you an elliptical, if you like, resolution on the sky. If you had a circularly symmetric telescope, then the resolution will be the same in both directions. So the best resolution that you will get in either direction is determined by the longest baseline in one of the directions. So for example, for the very long baseline array, what you will do is that you will take the antenna in Mauna Kea in Hawaii and the antenna in Puerto Rico in the Caribbean, and that's the longest baseline. So that determines the best resolution you can get in the VLBA. It turns out that the north-south baseline for the VLBA is not that widely separated. It's only about 5,500 kilometers, maybe 4,500 kilometers. So you have a very elliptical beam typically with the VLBA, where the resolution is very compact in the east-west direction, but is much fatter, if you like, in the north-south direction. And that's one reason that, for example, with the Event Horizon Telescope, which is used to make this image of M87, the Atacama Large Millimeter Array, ALMA, was so important because ALMA gave you a baseline now to the southern hemisphere. So even earlier, people were trying these observations, and there were telescopes in Mauna Kea in Hawaii. There were telescopes in Europe, which give you this nice east-west baseline. But there was nothing in the south. And ALMA suddenly gave you this hugely sensitive telescope in the southern hemisphere, which suddenly let you get this north-south baseline, which is as long as the east-west baselines. And so, yeah, it's a good question. An interferometer, if you want a symmetric interferometer, then you want the baselines to be roughly uniform in all directions. And that, of course, is not necessarily what happens. With the VLA or GMRT, that's kind of what happens because the antennas are more or less symmetric. You tend to have the same length in all directions, the same maximum length in all directions. but that's not necessarily the case.
Okay, thank you so much, sir, for answering all our questions. And
Prameet, just one moment. Hi, sir. This is Dr. Dev from the physics department at Thapar Institute. I would just request you share like one or two real life examples how our students, like engineering students, have contributed in one of your or two of your or your colleagues' project live in last like 2, 3, 5 years, so that they can get like with their knowledge right away how they can contribute, or at this moment they would only need to learn something, then they will be able to contribute. I just want your some comments regarding these things.
Okay, that's a very good question. So for example, the work that I showed you on atomic gas at high redshifts, that was done by Aditya Chaudhary, who is a PhD student in NCRA and who joined NCRA after his BSc. And Aditya is an outstanding student, of course, but he's one of many good students in NCRA, but he is truly an outstanding student. But that's the kind of thing. So Aditya has done the bulk of that work himself. He basically he spent the time understanding the 21 centimeter line. And we had already planned the observations, the original observations. So we knew the broad picture, but Aditya came over and he took on the project. So he spent the time learning the physics of 21 centimeter, learning radio interferometry, which he learned more or less himself, although with discussions with Jairam Chengalur and me. And then he did the imaging he actually wrote his own code. So for example, lots of engineering students are great at software and at writing programs, at programming. Aditya is superb as well at programming. And he came up with lots of interesting ways of handling the data, which I would never have thought of. I'm terrible at programming. And certainly I see that many students today are infinitely better than I am at programming. And that's often a very good way of getting into this. The other thing is that students, of course, learn much quicker than, for example, I would do at this stage. You learn much quicker when you're young. So somebody like Aditya, somebody like like one of the students at Thapar, would, if you're excited, if you're motivated, it doesn't take long to learn the basic physics and to start doing stuff. I've had wonderful experiences with my undergraduate students working with me during summer projects. For example, I had a student about 5 years ago, Avni Govardhan, who did a really nice project based on analyzing absorption spectra from the VLA. Again, she learned the analysis on the timescale of 2 months, produced good science results within 2 months. I had a BSc student, Parichay Mazumdar from St. Stephen's College, who was a second year BSc student. That was the same year actually, who did a great job of analyzing Green Bank telescope data. Again, the way you do it is that you kind of take steps. You take steps to get to learn more and more and more. You don't start by taking on a crazy problem. You start by doing basic things. You start by learning. And as you learn, you grow, and then you take on more and more challenging problems. And so, but even undergraduate students who are interested, who are motivated, of course, motivation is, I would say, a fundamental part of this. You have to really want to learn and want to push yourself, I think. And you have to want to learn about to know about the universe. And I've certainly found that undergraduate and master's level students have been excellent. I mean, it's been fun for me because, of course, you learn yourself when you're chatting science with students. You learn a lot of things yourself. You learn new ways of looking at the same thing that you thought about before from one point of view. When you have to explain it to somebody else, then you have to think about it very often from that person's point of view. So you benefit yourself from these discussions. And very often I have learned from students who have pointed out errors in my own thoughts on a problem because they're bringing a new perspective to it. And they're not biased by the information that they already have, but they don't have much information. So very often you come fresh to a problem, you actually bring an original perspective to it. So I have hugely enjoyed working with my summer students and undergraduate students in general, and also of course PhD students. So Aditya is a great example, but even for example Bornali Das, who did a 3-month project with me before her PhD, who's now doing a really nice PhD with Poonam Chandra. Apurva Bera, who is a master's student from IIT Kharagpur, who joined and did his PhD over here. Nirupam Roy, who was a BTech student many years ago. When I was a postdoc in the US, Nirupam was a PhD student with Jairam. and he had a BTech background. And he just learned the astronomy on the fly as he came in. At NCRA, we have a one-year graduate school, and then you do a couple of projects. And so you learn astronomy when you do your, on the fly, and you learn a fair amount of physics on the fly in the first couple of years of your graduate school. And then you learn what you need to learn, so to speak, to go ahead. And that's part of the joy of doing science, that you're learning every day. I'm learning stuff today, right now, and it's a pleasure. And I hope to be learning stuff till the day I die. I mean, I would feel very depressed if there was nothing to be learned, at some point of time. There's always things, always new things that we can learn. And so I think we all are students. Some of us are more experienced than the others, but being a student is a good thing. So I would say that, if somebody is motivated and excited about astronomy, they should come and join us, and it'll be great fun.
Okay.
And sir, just to be clear, these datas from, let's say, GMRT and all, they're all open source, right?
Yes. So the GMRT, I should say yes and no. One reason I love radio astronomy, I truly, truly, truly love radio astronomy, is that radio astronomy has what is called an open skies policy. On every radio telescope in the world, anybody, anywhere in the world can apply for observing time. So the way it goes is that you apply for observing time. You say, I want, for example, 20 hours of time to do some science project. This project will be evaluated by a time allocation committee. In the case of the GMRT, by the GMRT time allocation committee, at the VLA, by the VLA science panel, at the ALMA, by the ALMA science panel. They will evaluate your proposal and compare it to other proposals. They will rank proposals, and they will allocate time to the highest ranked proposals. And then the observation they carried out, either by you or by them, with your inputs. And then typically you have about a year in which to analyze the data. So there is what is called a proprietary period during which the person who came up with the science idea can analyze the data. And that is to protect that person. If somebody has had a good idea, then you don't want that person has the right to now push their idea forward. And that time scale is typically a year, after which the data are completely public, anybody can analyze them. And so, for example, it's been studied, this thing has been studied in the VLA and the GMRT. About 90% of VLA data, I believe, are unpublished, between 80 and 90%. And about, I would say, 80-90% of GMRT data are unpublished. So there's a lot of data in the archive of really good data that has not been published for one reason or the other. Sometimes the data did not provide the science answers that the person who was doing the science wanted. Sometimes the person who got the data couldn't do a good enough job of analyzing it. So the data are available for science by the public, by anybody basically, 1 year after the observations. In the case of the GMRT, 18 months after the observations. But the telescopes are open skies, which means that anybody can apply for time. And this is unlike optical astronomy, where, like say, for example, on the Keck telescope, only a certain set of people can apply for observing time on Keck. People from India, for example, cannot apply for time on Keck. You will not be allocated time. In the radio, anybody can apply for time on radio telescopes. And that's one thing which I really find lovely about radio.
Okay, sir. Thank you, sir.
Thank you so much, sir, for giving such an insightful journey of how we can get into research and start from. And sir, now we would present our screen.
Yeah, so I'll just stop sharing.
Okay.
Okay.
Before we proceed to the panel discussion, we would like to have a group photo. So if you guys can just turn your cameras on, that would be great.
I will admit I'm petrified of group photos. I see Harvinder there.
Next, in the panel discussion.
Yeah, hi Nisim.
Hey.
Magnified. This is Mamta on this side. Hi.
Hi. Hey, Mamta.
Yeah,
Long time no see.
exactly.
Thank you, everyone. Okay, so now we'll move on with the panel discussion. We are having the panel discussion with Dr. Jasjeet Bhagla, Dr. Nisim Kanikar, and Dr. Biswajit Paul. And Dr. Harvinder Jasal ma'am will moderate this panel discussion. It's on the topic alien life and exoplanets. Now, if anyone has any questions, you can just put them in this form. We are going to put the forms link in the chat box. Apart from that, you can also scan this QR code and this will open the link to the form. So we'll just put it in the chat box also. So if you have any questions related to this topic, so please scan the QR code and put it there. So now I would like to invite Suryansh. He's going to help with the panel discussion.
Greetings, everyone. Greetings to respected professors here. My name is Suryansh Tiwari, and today I'll be the student representative for the panel discussion. Before we go ahead, I have a request. As Ishita said, if the students that are visiting the lecture right now, if they have any, if they have any questions that they want to ask, as she said, please do put in them. Meanwhile, we have received some questions from the audience, and I would like to ask one of them before we move ahead. One of them, the question that I currently have, that I received, was that keeping time dilation and the huge light years distances between habitable planets which might have advanced life, is it really necessary that when and if an advanced life form does contact us, when they reach us, uh, would they be more advanced than us in technology?
Uh, Suryansh,
Yes, ma'am.
can I say something over here?
Yeah. Yes, ma'am. Yes, ma'am. Yes,
I
ma'am.
would request you to please hand over the questions to Dr. Harvinder. She'll take over from here.
Yes, ma'am.
Okay?
Okay, ma'am.
Yeah.
Yeah. So now, Harvinder ma'am will be starting the discussion with she asking the questions to the respected professors. Yeah. Harvinder ma'am, you have this stage.
Yeah. And if you get any questions in between, you can just send her on the chat box. Okay? Yeah, thanks.
Thanks a lot, Suryansh and Mamta. So let's start our discussion. And this is first, I wondered why we are suddenly having a discussion on aliens and exoplanets. But okay, it is related to the discussion we had in the morning. And it's also very important discussion as present because there are more than 3,000, actually 3,230 systems to be precise, in which exoplanets, in which these planets have been discovered, and more than 4,000 planets we know about now. And 715 of these systems are those systems in which there are more than one planet. And our panelists today are Jasjeet, Nisim, and Bishwajit. Two of you know, Jasjeet and me have been giving talks in Thapar. Bishwajit gave a talk in the morning, and Nisim just finished his talk. And of course, when the discussion on exoplanets comes in, you also talk about life on those planets. And probably I'll set the ball rolling by reading out some of the questions which were sent to me, which I categorized a little in a broad classification. And there is the sequence which I was sent them in. I will not follow that. I'll follow my own sequence, which I checked with Mamta. And maybe I'll start the ball rolling with Nisim, because in his last slide, summary slides, he had written probe of the origins of life via searches for complex organic molecules. So the first question that I will start is near home, not really an exoplanet, and that is, very recently Venus was found to have traces of ammonia. I think the question, the person means phosphine. Ammonia in its atmosphere, and it's widely considered to be a strong reason to believe in the presence of life on the planet.
Sorry,
or at least, yeah. Should I read the question again, Nitin?
Yeah, I actually, you're a little low. Can you just bump
Okay,
up?
I'll just. Am I more audible now?
Yeah. Thanks.
Yeah. So very recently, Venus was found to have traces of ammonia. I presume the person means phosphine in its atmosphere, and it's widely considered to be a strong reason to believe in the presence of life on the planet, or at least in its clouds. What would your take be on that entire thing? Could there actually be life there? So this is the closest home question that I have, right?
Okay, so that's I should mention that claim detection of phosphine is being questioned right now. That's step one. There are other people have analyzed the same data and are concerned about. The one problem with things like phosphine is that these are lines in a region of the spectrum where there are many other lines. And so when you identify a line, you have to be sure that this line is a line from the molecule that you think it's from. And that normally means identifying multiple lines from the same molecule. And it can be hard because there are many lines. I mean, the most famous example of this is this very famous prebiotic molecule called glycine, which people have claimed many times. So anyway, so phosphine is possible. I would say the jury is out as to whether the phosphine, the claim detection is real or not. That's step one. The second thing is, suppose you saw phosphine, does it necessarily imply life? That I would say the answer is almost certainly no, at least from my point of view. I would be very skeptical. Venus is on the edge at best, and probably not even really on the edge of what is called the habitable zone, the region where you can actually have the formation of water, of stable water. And so Earth and Mars are the only planets in the solar system which are within the habitable zone. Mars is a little bit, it's on the edge. And Venus is not close to the edge. It's a little bit, it's too close to the sun, basically. So I would be very skeptical of the notion that Venus could have had stable life forms, even if the phosphine were confirmed later.
So let's just summarize in the way that the same data, same techniques, and it has to be confirmed.
Yes, it's also, in fact, it's even more complicated than that, because you might need to get new data. For example, even if the lines are real that they've seen, you almost certainly would like to get other lines. So now suppose you see a line from phosphine. Phosphine has multiple complex lines. It's got a complex line spectrum. But if you identify two lines, you need to be sure that those lines are really phosphine, because there could be other lines from other more complicated molecules or less complicated molecules with the same frequency. Because that part of the spectrum is a mess. I mean, just to give you an example of how messy it is, a survey was done of Sagittarius A, or Sagittarius B2, sorry, a really powerful molecular cloud in the galactic center region with the Iran 30-meter dish. And they detected about, I don't know, some many hundreds of lines, with nearly 1,000 lines, if I remember right. And about 20% of those lines have not been identified in the lab. We don't know what those lines are. So there are lots of spectral lines in this millimeter range that we don't know. They're just very complicated molecular lines. And we don't know what they are. We've seen them in astronomy, and we've not seen them in the lab. And so this is really difficult. When you see a set of lines, the way you will be sure that's really a phosphine line would be by taking the phosphine molecule, making predictions that, okay, if these lines are phosphine, now you can make a prediction for, say, 3 or 4 other lines, or at least one other line at a different frequency, and go and look for that line. And so even the same data may not be sufficient. To be honest, I have not looked at this thing in sufficient detail, but one should be wary of complex species because of this issue.
Biswajit, what's your take on this? Biswajit? Okay, meanwhile, Jasjit, could you add something if you want?
Not really. I think Nissim has covered the ground in the sense that we don't know whether the line has actually been detected or not. There is no confirmation of that. Other people don't find the line in the same data. And B, even if the line is there, it is not clear whether the origin of it is organic and related to life. So there is caution on two specific grounds over here.
Yeah, I noticed Biswajit had switched on the mic in between. Could you, Biswajit, are you there? Okay, meanwhile, I'll read out the next one, which is again on alien life. So question is yeah, Biswajit, you want to add something to the previous question?
Sorry, yeah, I just did a very quick lookup because I just want to confirm my memory of this thing. And the thing is more or less what I was saying. In fact, it's even worse than what I was saying. I was probably too positive about the thing. So these are ALMA data, and they have exactly one spectral line from phosphine. And there is there was tentative evidence a long time ago from the JCMT, the James Clerk Maxwell Telescope, and then they analyzed some archival data from an old Pioneer, I think Pioneer, the spacecraft. But basically, the lines are the old lines are very weak and not really believable, and the ALMA line is one line. You would never believe anything based on one line. So I'm even more skeptical now than I was 5 minutes ago. I had a vague memory of this, but yeah, I thought I should just check.
Yeah. Okay. I'll again ask Biswajit, probably, I don't know, I haven't received okay. Maybe I'll go to the next question then, is again on alien life. So question is, our search for alien life focuses on the existence of materials and resources we need to live, such as air and water. Are these methods other than just looking for biomarkers which can be used to, are there methods other than just looking for biomarkers which can be used to detect life on other planets? I think this is, part of this question has already been answered, but I think I'll leave it to you to start up. One, of course, we have already discussed.
Biswajit, Jasjeet, would you like to go?
You can start on this. Yeah.
Okay.
I'll pitch in. Yeah.
Okay. So there's two ways in which you could look for life. So, okay. So let's take a step back and ask the question of what exactly is this life that we're talking about. You need to define what life is before you say, let's go looking for life. So the life that we know of on Earth is what is carbon-based life. It's long-chain carbon molecules which combine together to form organisms that can support, for example, electrical reactions between the organisms, electrical currents within the organisms. And, for example, carry out chemical reactions, for example, in plants to feed themselves, let's say, to convert, to do photosynthesis, for example. But the broad basis is carbon chain molecules, right? It's organic chemistry based on carbon chain molecules. The other atom that you could think of that might produce similar long chain molecules is silicon. These are two atoms that we know of that could produce long chain molecules and which might form the basis of say, intelligent life, let me say. So where you could generate complex large molecules which would normally be considered a requirement for intelligent life. So now you could ask the question, hang on a minute, what are people looking for? And so the way you could do this is to say that, okay, let's look for life of our kind. And by our kind, I do not mean humans or animals or plants. It means carbon species. So long chain carbon molecule based forms. You could do things like biomass, things you could look for, again, carbonaceous molecules, if you like. And the third thing you could do is to look for things such as signals that you would not expect in nature. So, for example, as we did about 20 years ago in the Pioneer spacecrafts, we had recordings of Kesarbai Kerkar on the Pioneer spacecraft sent out, and other people as well. But so if some alien life form a long way off meets the Pioneer spacecraft, it is extremely unlikely that somebody could produce sounds like Kesarbai Kerkar in nature as in without intelligence. And so that would be a signature. So you could, or somebody could build the Pioneer spacecraft. It could be random. Somebody could build, it's not the right term, that it could be randomly assembled together. So those would be a signature. You could look for signals, direct signals from an extraterrestrial civilization. So those are the three, if you like, ways of looking for things. You could look for planets in the habitable zone and then target them. You could look for signals of biomass, carbonaceous forms. And three, you could look for direct evidence of life and of intelligent life, which would be signals which are not natural. The first two are natural. So those are the three approaches I can think of. Silicon life forms are even more complicated. The third approach, of course, still works, but what are the kind of signals that you would see from silicon biomasses is unclear, at least to me. So carbon life forms, simpler. So the answer is yeah, those are the, looking at biomasses are, if you can form complex biomasses, then there is at least a chance that the process which gave rise to that complexity could also give rise to intelligence, self-awareness, if you like. And so that seems like a reasonable approach to looking for intelligence. Because if you like, searching for intelligence directly is almost a needle in the haystack problem. You don't know where to look. If you get lucky, of course, if somebody comes and whacks you on the head and says, "Hey, look, I'm superbly intelligent," then you're set. But as you know, the question was asked in the beginning, if somebody can get to you from a long way off and tell you that, "Hey, look, I can get to you," the chances are that's an extremely advanced civilization. It's not very clear if you really want to be an extremely advanced civilization. Chances that they will treat you like, irrelevant species is not negligible, to put it mildly.
Or maybe a colony. Yeah.
Sorry?
Or maybe a colony.
Or wipe you out. I mean, if you look at what humans have done historically, that's not very different from what the way we might be treated. So one should be careful. So the problem with detecting signals from very distant objects directly is that it's hard. Where do you look? So, for example, the Arecibo telescope, since the 1960s, after Frank Drake came up with the Drake equation in 1961, Arecibo has been pointing at all kinds of stars which might have planets, hoping to find some signal which cannot be explained simply by emission from the star or the planets themselves. No signals have been seen so far. And people are still looking. So, for example, the SETI project, which is doing similar searches with Arecibo and the Green Bank telescope, Yuri Levin has given about tens of millions of dollars to GBT in Arecibo to carry out what is called the Breakthrough Listen project, where again you point at star-forming regions and you listen for radio signals. Because again, radio signals are not very easy to produce in nature. Pulsed radio signals are not very easy to produce in nature. So people are trying to look directly for life, for intelligent life, for evidence of intelligent life. And so far, we haven't seen any evidence for it. And so an easier way may be to identify more and more biomass and then target those locations. Sorry for the length.
Please, Vishwajit and Jasit, would you like to add something?
Am I audible?
Yes.
Yes.
So among students who are interested in exoplanets, various aspects of exoplanets, I would say, searching for intelligent life elsewhere, possibility of aliens, possibility of communicating with them, etc. I think we are not there yet to, make meaningful progress in these directions today. There are a lot of interesting astrophysics of exoplanets themselves, planet formation, planet migration, and so on and so forth. I think that's the area where much of the science progress and science interest is. Finding habitable planets, finding things about atmospheres of planets are areas where a lot of progress is being made. I would particularly take names of, for example, let's say planets around binary star systems. There is a lot of interesting astrophysics there. Formation of planets, migration of planets, how does a planet influence evolution of binary stars, and so on and so forth. So people who are interested in planets, I think there are a lot of other interesting research areas today which are viable, rather than trying to establish connection with aliens or worrying about when do we get in touch with aliens. So the focus probably can be a little bit shifted in the right direction.
Thanks, Vijay. Jasit, would you like to add something on this?
Yeah. So amplifying a little bit on what biomarkers or markers of life there may be. One of the thought experiments which was done around 45 years ago was to ask that suppose someone could take spectra of the Earth, then would they see any evidence of life? And the answer over there was that the coexistence of methane and oxygen tells you that one of these is being produced, and methane being in smaller quantities is indicative of some source, does not immediately identify itself as a biological or a life-based source, but that is plausible. Uh, to add a note of caution to that, similar reasoning was used in mid 1970s to claim that Jupiter has lightning and thunderstorms, because they identified species of chemicals which cannot coexist, and things which require enormous amount of energy to generate. So unlike methane, which has a very low binding energy, we were talking about molecules which required several EVs, and therefore the argument was that Jupiter must have lightning and thunderstorms, and these were indeed discovered in late 1970s by Voyager and Pioneer experiments. So looking for chemical species which ideally should not coexist is indicative of something happening, some either some energetic chemical reaction or life, and these can be the first step in trying to move towards identifying life. So this is to be done remotely. If we go back to first landers on Mars, Viking landers, there were a whole bunch of experiments which were carried out trying to see whether there is life on Mars or not. And they had one bunch of experiments which looked for complex organic molecules, and another set of experiments which looked for presence of metabolism. Curiously, the experiment on metabolism found that there was indeed some metabolism happening in soil on Mars, and this was reproduced in the sense that Viking 1, Viking 2, which landed at spots which were 4,000 kilometers away from each other, both got positive. On Earth, before the launch and before finalizing design of the experiment, the same thing had been done in a large number of places. Controls had also been done, for example, taking some soil and baking it at high temperatures to kill off everything and then repeating. And none of those gave a positive experiment. There are a few explanations, chemical-based explanations, which do not require life, but still, even that thing is not completely settled. So over there, of course, they were looking at two different aspects of life. One is presence of complex carbon molecules, which drew a negative. The other was metabolism, which drew a positive. So as Nissim said, one needs to define what is life before one can design experiments and move further. And one can see that definition of life becomes overly complicated if we try to avoid traps of various kinds.
Yeah, and we do not want to get into the phosphine-like situation we are in right now also, right? Okay, next question is related, and I think the answer to it has already been given. If life thrived underground/underwater, then there would be next to no biomarkers. Then how would we identify such life? I think that question is also a little bit doubtful now, but could you take on it?
Sorry, if life were underwater.
If life thrived underground/underwater, then there would be next to no biomarker. Then how would we identify such life? So I don't quite understand this. Why shouldn't be there any biomarkers now? So I think the previous question answers to that already tackle a lot of things in this.
And the biomarkers would be in the atmosphere of the planet, and they would be things like oxygen and methane and water vapor. So if you see those, that's telling you there's a very good chance of intelligent life there.
Yes.
Also, there'll be energetics in the sense that any life will have some consumption of energy, which will always be inefficient, and therefore there'll be additional heat coming out of somewhere which you could not account for otherwise.
So I should mention also that the JWST, the James Webb Space Telescope, which is being launched next year, and the next generation European ELT, especially, and also the TMT, if it's funded, the 30-meter telescope, will be able to actually search directly for these biomarkers in exoplanets. The problem, and this is something that people should be wary of. there are many you really need to worry about theoretical models. I think Jasjeet's emphasis on the fact that the explanations, for example, of lightning on Jupiter, the simplistic explanation is just one of the possible models. So you really have to use theoretical models and be very careful about interpreting your data. You may see something, but that may be consistent with what you expect from one model, but that does not necessarily mean that model is correct. But experiments will be done certainly over the next decade or so.
Biswajit, would you like to add something to the discussion?
No. Carry on.
Okay, I'll move on to the next question, which is now continuing, but the theme slips sideways now. Do you think any sort of life, carbon-based or otherwise, could survive on rogue planets? This is a slightly difficult question, I would say.
On the rogue planets?
On rogue planets, yes.
Okay,
these are planets which are not around any star.
Not in any of
them. That's the usual definition of rogue planets. Okay, so I would say the answer is no, in a pointed way. Just simply, I mean, a lot of the source of the energy on any planet, that's the reason you have the habitable zone, right? You have to be at the right distance of the planet, otherwise it simply gets too cold for reactions to happen. So it would be very surprising if a rogue planet which did not have a source of energy like a star could sustain life for, even if it started to have life for a short while it was near a star, where would it get the energy form to maintain it? So I would be very skeptical of such a notion.
Unless it became rogue after they reached a sufficiently advanced technological state, so that they do have access to energy generation.
So then you need to do real fine tuning. It needs to be rogue, but not very rogue.
But considering how much of fine tuning is required to have life on Earth, life on Earth already depends on so many coincidences. Perhaps on a rogue planet, if you depend on different kind of chemical, for example, if it's not carbon-based, silicon-based, and if it's not energy source from a star, but which is geothermal or something like that, probably you depend on a few more coincidences to support life on a rogue planet.
It's possible, but very unlikely. I mean, people have worried about, for example, things like super Jupiters. But the problem with super Jupiters is that they're gas giants. So, sources which are, slightly less than a star, which produce lots of energy themselves, are not very good at supporting life, that at least the kind of silicates or carbonaceous life forms that we think about. So it's unlikely, I would say. Jasjeet's model of a star, of a planet escaping from a star is probably more likely. But the catch over there is that, again, if you think about the Earth, it's taken 5 billion years, 4.5 billion years to produce intelligent life, let's say, in the life of so it's taken a long time. And so now, if you escaped from your star before that happened, it's the amount of time that you have to produce that intelligent life, which could now produce self-sustaining forms, is not very much. And so I'm skeptical. I mean, I think your point earlier, Biswajit, that look, we don't have a damn clue, is a good one. And so I think the truth is really that, if we see something, we'll say, whoa, fantastic. And then we'll go and say, this could have happened all along.
Yeah, I would think searching for life is far too away. Currently, habitability is the closer goal.
Yeah. But I guess this has a relevance to habitability in a sense that if you have observing time on a telescope, would you point it at a rogue planet, or would you point it at a planet around stars? So would you get observing time to point your telescope at rogue planets? Because you're talking about hundreds of hours of time again. So my suspicion is that time allocation committees would tend to support projects searching for habitability. The habitability is likelier around stars.
Yeah, and cold giants are coming, so just wait for it. Next question is, what about planets that exist in the Goldilocks zone of their star, yet still have extreme environments, like planets made up almost entirely of water, or massive planets with a lot of gravity? This is part one of this question. And should we tackle this, or should I read out the full long question?
You could go ahead.
I think I'll read it out. Could intelligent life be harbored on these planets? If so, how would said intelligent life attempt to leave its home planet? Now, same question, but we have discussed some part of it. So they would like to leave the planet now.
Is that because they will be asked lots of questions about life on other planets?
They have to be intelligent life. That's what they're saying.
So just go over the first part. So there are planets in the Goldilocks zone, and
of their star, yet still have extreme environments like planets made up almost entirely of water, or massive planets with a lot of gravity.
Okay, so what is the problem? The Goldilocks zone is defined as the region in which a distance in which water will stay in liquid form. Hello.
You are audible, Nisin. No problem.
Sorry. Yeah. So you have other regions in the. You could, in principle, have regions have planets in the Goldilocks zone where water is in liquid form. It is unlikely that you will ever have pure water planets. That would require a really strange. I mean, planets form typically from protoplanetary disks around stars, and it would be very surprising if you would just produce 100% water planet.
It's almost entirely is the word used here. So
yeah, but almost entirely.
Yeah, I mean,
10% is a lot in terms of mass.
So probably the question meant liquid surface.
Liquid surface is fine. Yeah. Liquid surface. In fact, that's the definition of the Goldilocks zone. That basically you have a lot of water. So yeah, you could have a planet with a lot of water, and you could in principle have life happening in that water. It could be.
Yeah. So they are worried about discovery of fire if you are going to stay in water all along. I'm trying to second guess here. Yeah.
Yeah. So the thing is that we are assuming certain things that, given our background on the planet Earth, that this is the natural way in which you will approach intelligence. That may not necessarily be the case. So, I mean, just to give you a horrible example, we know that in the oceans on the planet, there are vents from the center of which come out at the base of the oceans, where there are life forms which have never actually seen the sun, which are actually deriving their energy from, if you like, from vents in the base from sources of energy inside the Earth. So maybe you'll pick up energy from there. Maybe you will. I mean, these are all big maybes. So I'm not terribly concerned. Second thing is that the probability is again very low. If you simply have water covering the entire surface of a thing, you need to have you need to be thinking of a nice uniform sphere to have that kind of a thing. In reality, you'll have corrugations, you'll have structures where a liquid will collect more efficiently and places where it won't collect more efficiently. So I would tend to not worry about these things. I would tend to go back to Biswajit's point, which I totally agree with. We don't have a damn clue, and we should just go and look. If you're excited about it, go look. Don't take your biases too far, because we don't know what we're going to see.
Yeah, he also mentioned that there are experiments.
Thinking.
Biswajit?
Yeah, so searching for habitability, searching for presence of some form of life is one thing. Trying to link that with or even think around when intelligence may evolve, when technology may evolve, and so on, I think are very remote questions. One needs to necessarily dealing these. Even in, even on Earth, if you see modern technology is few hundred years only, right? Our understanding of much of physics, chemistry, and science is also few hundred years. So in a perfectly habitable planet where life form has evolved to very high level, even.
You've gone mute, Biswajit.
Can you hear me now?
Yes.
Yeah. So I was just really saying that on 4.5 billion years of solar system, intelligent life, or that could be identified as having some sort of intelligence and technology is for a few hundred years only. So habitability and some sort of maybe even complex life form, searching for that is one thing. Looking for intelligence or looking for technology is quite a different thing. So we need to make a distinction between that.
This also brings me to the next question, in which it's related to the previous ones. Can we have moons of gas giants support a rich variety of life despite not being in the Goldilocks zone? So that's also, I think, another question which is related to the previous one. Do you believe we have hope of finding life on our own gas giants, Saturn's moons like Titan? While it has been called a profitable habitable zone by NASA, there seems to be no visible sign of thriving life on Titan's surface. Do you think its deep methane-rich lakes could potentially harbor life? If yes, how would our space agencies be able to confirm the speculation? I think the answers to these are almost there. We have discussed all these, but I think we can still discuss a little bit on, despite not being in Goldilocks zone, can they harbor life?
So moons of Jupiter or Saturn, wherever you have some sort of liquid, whether it is water or methane, certain life form formation and evolution of certain life form cannot definitely be ruled out. Whether coming days investigations will lead to that or not, we will have to see. There is no apparent reason to rule out, wherever there is liquid and a suitable chemical, that life would not form. But again, whether the life, how evolved the life form is probably a very different question. That depends on the evolution history. When are you probing? When are you getting in contact with them?
Jasit, you were saying something?
No, I agree with what Biswajit has said. Having an atmosphere and having some liquids present on the surface are important, because they allow chemicals to migrate, and presence of these is also indicative of a reasonable temperature, in the sense that whatever life form is, you do require chemical reactions, and we know that the rate of chemical reactions is sensitive to temperature. And so the Goldilocks zone may be derived from possibility of having water in liquid form, but going too far away from it will also take you to either a stage where you don't have molecules, stable molecules at a given temperature, and on the lower side you will get into a regime where the chemical reactions are so slow that the time scales of what we consider life will be unrecognizable, to say the least.
I think that point is the critical one. The fact that we have only 13.5 billion years in which to produce some kind of life, and so if you're on an object where the timescales are very, very slow, the probability of producing life in that object is almost by definition much lower. So again, from the point of view of since I am an observer, from the point of view of convincing a time allocation committee of giving you time to search for planets around, moons around, things like Jupiter, super Jupiters, the probability of getting observing time is lower than if you were looking for things around things like M-dwarf stars, for example, or G-type stars, but M-dwarfs would be even better probably.
And we have already discussed how to communicate with such life forms, and someone has said that yeah, but they haven't yet tried to contact us. And there is this cartoon also that no intelligent life would like to contact us probably. So I will skip that question, and I will come to a question which is interesting in some sense. What are your opinions on the origins of the mysterious quote-unquote asteroid Oumuamua, which some claim is an alien ship as it behaves differently from any interstellar object that we know of? Would you like to add something to it?
Yeah, so we know of precisely two interstellar objects so far. One of them is a comet, the other is Oumuamua. And from the looks of it, it is an asteroid. It's somewhat oddly shaped. moving very fast. But other than that, all the efforts to probe it and look for some sign of an intelligent design or radio transmissions, they have all failed. So as far as I can tell, it is simply consistent with being a strange asteroid. And we haven't seen such things earlier simply because we didn't have the capability to look for them. It's only in the last decade that we have started periodic all-sky surveys with facilities such as Pan-STARRS. And now with LSST and the Palomar projects, which are there of an equivalent kind, we are starting to essentially survey the entire sky, going to unprecedented depth and doing it once a week. And that is why we are able to detect such objects and detect them fairly early so that some follow-up can happen. So I think there are plenty of things of this kind which will be discovered in coming years and decades as we look more carefully.
Anything to add to this?
Yeah, I think
No, nothing.
I think that's a really good summary. In fact, there are estimates, rough estimates. So Oumuamua is special in multiple ways. One is that it's got a funny length to width ratio. It's got a very large length for its width. So you wonder about how such an object could be formed. It's very rocky, very, very rocky. And it varies in brightness as it spins. So all of which are interesting, but they don't make it particularly special. They make it special. I think Jasjeet's point is that the reason we are seeing these objects is that finally, with the Pan-STARRS telescope, we're actually doing these all-sky surveys, and so therefore you have a chance of seeing these faint, transient objects, and we'll see far more of them. In fact, people have estimated that things like Oumuamua should be detected roughly once a year with things like Pan-STARRS. So we expect to see more of these as you do more and more of these observations. And so, it's not surprising that every so often you will see an object which is genuinely interstellar heading towards us. And it could well, it has properties different from asteroids, from known asteroids, but that does not mean it's not an asteroid.
Yeah, that's what I was coming to. Its shape is rather different from any asteroid we see. Yeah.
But the thing is that the formations of asteroids are also fairly complex. It's a distant asteroid. It seems reasonably possible that it's been stripped by radiation from cosmic rays. So now you have to worry about the formation processes of these things.
So much more work and study needs to be done, and maybe wait a little. Maybe we'll find more similar objects, and probably, yeah.
People who want to look at the more speculative side of it should definitely go and read Rendezvous with Rama by Arthur C. Clarke. To give you an interesting connection, when Oumuamua was discovered, it's before the formal name was given, the working name was actually Rama 3.
I will start reading the Zoom chat questions now. I just noticed that there are many now coming in, but before that, what are your thoughts on the existence of the disputed planet 9? Meanwhile, I'll just collect the questions from the Zoom chat. Planet 9.
Thoughts in what sense?
So whether you existence, okay, this is thoughts on the existence of the disputed planet 9. I think this question we can leave a little probably. What do you say? And we'll go on to the other ones which are more precise.
Yeah, people
come back to it later. Yeah.
Yeah. So people have. There is evidence, tentative evidence for it. We can probably dispose of it quickly. There's tentative evidence for it based on planetary orbits, but there's no strong evidence for it. And people have been talking about there are jitters that you see in the orbits of the planets. That one explanation is that there is an extra body which is on a very large orbit, very elliptical orbit around the sun, and which is much further away. And that's been the one model. But other people have come up with other ways of interpreting it. So it's just one model, and there's no strong data one way or the other, I would say.
Okay, there is one interesting question which has come in. Some of the other questions which came in the Zoom we have already tackled. One question which I thought I would like to read is mimicking Urey-Miller experiment. Why don't we experiment ways to try to produce silicon-based life and observe its behavior so as to broaden the basis of our understanding of quote-unquote life in general and help us to search for extraterrestrial life elsewhere? Mimicking Urey-Miller experiment. So do you have any?
Yeah, it is an interesting thought.
Yeah.
It's complicated. You need to produce a soup of silicon-based chemicals. And then, I mean, the Urey-Miller experiment is kind of, you need to produce a bunch of silicates and some form. Yeah, to be honest, I'm not even sure if I know what this has been tried in the lab, but just passing electricity through a bunch of silicates to see what happens. But I have a vague memory that they did find that you could produce I mean, okay, so I know you can produce long chain silicon molecules. Whether it's been experimentally shown via things like this, I don't think so. I don't have a strong memory of it. But there's no obvious reason why you can't do it, why you can't do a test like this.
Yeah, I agreed. I did chat with someone who works on this kind of experiments. So they also said that, we haven't tried it. So they didn't know the answer straight away. Someone working in astrobiology and chemistry of the early planets.
I think life is complicated enough with carbon life forms that it seems that, searching for signatures of things that we understand may be easier than searching for signatures of things that we don't even understand.
Okay, so there is one question which is to Nissim. Searching for carbon-based life forms would be the best approach to take while identifying alien life. Is there any progress in this field as of now? I think we have discussed this, and I don't think more can
Kind
be
of.
added right now.
So I can tell you something which is interesting, which is going on with ALMA. I would kind of be a little wary of this whole notion of alien life. I think I agree with Biswajit that I think alien life is for me not a really good astronomy question. It's just too out there. People search, but yeah, and if that excites you, great. But in classical astronomy, I would say looking for organic species, the building blocks of life is much more interesting. And so one of the things that's been happening over the last 20 years, we've been involved in this peripherally, is to look for more and more complex organic species and to ask the question of can you form the species that give rise to life as we know it in the interstellar medium. And so we found more and more and more complicated species via observations at millimeter wavelengths. We, as in not me personally, but millimeter wave astronomers. We've done things like mapping acetaldehyde, which is a complicated molecule. But the big thing that we still do, so people have found, aldehydes, ketones, alcohols, all kinds of, even fullerenes in the big proteins, for the simplest proteins, the simplest amino acids. And the classical amino acid for this is called glycine. It's the simplest of the amino acids, which are the building blocks of proteins. And so searches for glycine have been happening for about 20 years or so now, more than 20 years. We did some searches and didn't see anything. And there have been claimed detections, which turned out to not be real. And so that's one area where people are really trying hard to look for signatures of this prebiotic molecule, this very basic amino acid in the interstellar medium. The idea being that if you can form molecules like glycine or alanine or the various amino acids in the ISM, it becomes much, much, much easier to form proteins in protoplanetary disks in star-forming regions around stars. And so if you can find glycine, that would be a big step towards saying that, yeah, it's, the probability of forming complex proteins shoots up. If you can't form it in the ISM, then you're really saying that, okay, even things like amino acids had to be formed on planets after the planet was formed. So timescale has become much more of a problem. So I think that's the big step that people are taking right now in looking for organic molecules.
Yeah. Any addition to what Nisin just said? I think that's a fair point that, okay, it's better to look for organic molecules and rather than worrying about intelligent life and whether they're trying to contact us or right now or not. So let me just take a couple of more questions and I think we'll leave the discussion open after that, maybe. I think we are more or less done with the questions that were there, and we have basically answered many of the questions which are coming on Zoom chat to me. Okay, so one is a molecular cyclopropionylidene was observed in Titan, and it has not been observed anywhere. What's your view on that? So, what's your take on it? I mean, this is one question which has come on Zoom chat. I don't know how to pronounce it. Sorry, I'm bad at chemistry. Propionylidene. Yeah. So if you know about this, could you add to it?
No, not in particular.
It's the same organic molecules, looking for them,
Yeah,
right?
yeah. So you see complex organic molecules.
Yeah.
The solar system is very close by. So sensitivity is often one main primary reason. The second thing is that things like our satellites have gone and Huygens, for example, Cassini have gone very close to these planets, and so using these satellites you can actually observe complex organic molecules in the atmospheres of these planets, which you would basically never be able to do for distant objects. So it's not very surprising that you see complex organic molecules on things like on things like Titan or Ganymede or Io, especially Io. It would not surprise me very much, at least. It's a combination, perhaps, probably of sensitivity and local conditions.
Right. Any addition, Vishwajit and Jasdeep?
No, not on this.
No.
I think one question which I think could be useful to students is, what is the prospect of Indian research on the field of astrobiology? I think people are working on that. And Nadikar himself has worked on astrobiology. So are you aware of more projects which are happening in this field?
Sorry, who is that for? No, I think you're muted, Arvinder.
Sorry. The question is, what is the prospect of Indian research on the field of astrobiology? This question is not directed in it's for the panel in general to answer.
So I work in high energy astrophysics, which is probably farthest from life. In this area, of course, definitely there is no prospect of studying planets per se, and definitely not about habitability or life. However, I would like to just briefly mention that about a few years ago, we had serendipitously discovered a planet around an extra-binary system that was completely unexpected. An eclipsing extra-binary. We were looking at it to study the orbital evolution of the system, but then we found that the eclipse of the binary system was arriving at an oscillatory manner, and that led us to believe that there is a planet very far away, about 25 Jupiter mass planet or brown dwarf, if you would like to say, at about 5 astronomical 5 AU distance. So you do get linked to this field even when you work in a very different area. So there is a lot of serendipity in astronomy. What will link to what is difficult to say in advance.
Biswajit, you're muted again.
As of now, though we do not have a concrete astrobiology program, but things might evolve. Especially probably TMT would give us some opportunity when that starts.
So TMT's mid-infrared thing would give you a huge thing for a huge fillip for astrobiology. There are people doing things in exoplanets. For example, the TIFR group has Gagan Narang, Devendra Ojha and company. They've been trying to use GMRT to observe planets around M-dwarf stars. For example, very recently this year, Harish Vedantam and company with LOFAR discovered emission from this GJ1151 M-dwarf, which they argue is because of like a Jupiter Io-like interaction, cyclotron emission from the planet, from the star and the planet together. And so people like Narang and Gagan Narang and Devendra Ocha are trying to do this with the GMRT and other exoplanets. Jairam Chengalur and I have been fooling around with things like organic molecules, but although we haven't done it in the last decade, but we are vaguely interested in it. But yeah, and I suspect there are other people also doing things like searching for exoplanets, but it's not a large community, certainly not in India. There were proposals, if I remember right, for the Devastal. So now the Devastal 3.6 meter telescope has come online, and so people will probably be using that. I mean, I think there were proposals even from the Indian community to use that to either model or to study exoplanets. And I think Shudojit Sengupta at IIA, he has been doing studies of exoplanets.
Sujan Sengupta.
Sujan Sengupta, I beg your pardon.
Yes. For example, PRL has developed very high resolution spectrometer, which is useful for measuring masses of planets.
So there are groups. Astrobiology is a little more complicated, but there are certainly groups for exoplanet studies.
Yeah, I think we also need an intermediate bridge in the sense that we do not have too many people working on astrochemistry. PRL has a group, but other than that, we have very, very little.
Yeah, there are people now. I mean, for example, people like Bhashwati Mukherjee at TIFR, Manoj Purvankara. I mean, the thing from astrochemistry to astrophysics is kind of, as Nisijit is saying, we shift very smoothly from one field to the other without noticing in astronomy. And so if you're observing complicated molecules in a galaxy, before you know it, you have gotten into the dirty waters of astrochemistry. So, but there are people like Sarita Vig, even Swarna Ghosh, for example, has done a fair amount of astrochemistry. Even people like Devendra Ojha have done. Certainly, I would classify it as astrochemistry. I don't know if an astrochemist would classify it as astrochemistry, but that's their problem, so to speak. So there are people who are doing some amount of astrochemistry, I would say, in India, but perhaps not as close to lab chemistry. No, perhaps not like, say, people like Eric Herbst, who's one of the leaders of astrochemistry, but who do kind of things on the border of astrochemistry and astrophysics.
Because here at ISA, we have had a whole bunch of students who are interested in astrochemistry and who, after scoping around, go for chemistry major rather than physics major as a channel. And they have found good opportunities. So clearly, there are tracks which we have never explored, which exist for them.
Yeah, one of such students has done a summer project on radio astronomy earlier. So Nisim would know her. Divita Gupta. Yeah. I think we have covered quite a broad base in the questions, and I'm sorry if I haven't taken some more questions on immortality and stuff like that. But thanks a lot to the panelists, and I would like to, if you have any, could you please, if you want to add anything to the discussion, you're most welcome. And otherwise, I will hand over to the task volunteers. Fine. Okay. Okay. Thanks a lot to the panelists, and over to you, task volunteers.
Thank you, Arvinder.
Thank you.
Thanks, Nasim. Thanks, Vishwajit. Thanks, Nasim.
I would now like Mamta ma'am to come up if she wants to and give a vote of thanks to the speakers.
Yeah, hello everyone. Thanks a lot everyone for a very fruitful discussion. I am really glad that many of the questions from the students could be answered, and of course in a positive manner. I hope they are pretty well motivated now to actually look into stuff for themselves and have a fair amount of idea that what kind of opportunities do engineering background students particularly get into working in astronomy. Uh, I would like to thank all the speakers for the day, beginning from Dr. Brajesh, then Dr. Bishwajit, and Dr. Naseem, and of course our panelist, Dr. Jasjeet, who joined later in the panel discussion, and Dr. Harvinder for the moderating the session. And yeah, it was a very pleasant discussion, and thanks a lot for taking out your valuable time and giving your feedbacks on the questions. So yeah, I can hand over. That's all from my side. So thanks a lot, and I enjoyed the day. I hope everybody did.
Thank you.